Okay. So good morning, everybody. We are slowly gathering, but I think it's time to get started now. And thank you all for being here. There are more people connected on via streaming. So the whole event of today will be broadcast that way. As a first thing, we will have a welcome from the president of the CNR research area here in Milano Bicocca, Dr. Maurizio Maldini. Thank you.
Okay. Good morning to everyone. I'm very happy to be here at the University of Bicocca to officially welcome you all to the Roadshow 2014, an initiative promoted by the president of CNR. I want to thank and welcome all the speakers. They will show us some research opportunities available in some large-scale European facilities, and they will explain the research they are carrying on, and more important, at the end of the day, will be know how to access at these facilities. Thanks also and a special welcome to Professor McGreevy, Director of ISIS. He is going to have a talk about science at ILL and ISIS. I must also thank the Bicocca University that is hosting us in this beautiful conference room, Professor Andreani, that she is organizing this roadshow in all around Italy, Professor Gorini that for organizing this roadshow here in Milan. Okay, I don't want to take more time. Thanks again for coming.
So now we will start the first session, and the first speaker is connected in a video conference from Grenoble. So if we can switch on the connection.
Wait. First I say good morning before presenting the slides. I am Fabio Comin. I'm the responsible of the scientific infrastructure group here at the European Synchronous Radiation Facility. I was at the CNR in Italy, in Istituto di Struttura della Materia, and I came here for a couple of years at the beginning of the story of ESRF, and then I didn't manage and I stayed much longer. This is in a nutshell my story. So let's see now the presentation of the slide. What I have to do is just to give a large panorama of the science that you could you could do in the future in facilities like ESRF and Elettra. Now, ESRF and Elettra are referred as synchronous radiation facility, and both of them, often you call it as super microscope. Super microscope because you can see the invisible, and we will see in few minutes why. First, how many facilities? Oh, this introduction, of course, is for people that, in principle, is not user of synchronous radiation. So I apologize for all of you that knows quite well synchronous radiation and the world of facilities. So synchronous radiation facilities in the world, there are, let's say, 50, 60 facilities in the world that are spread essentially in the North Hemisphere, but there are also two exceptions, one in Campinas in Brazil and the other in Melbourne in Australia. But all of them, they have the same characteristic. Of course, there are differences between them. I will say a few words more about two of them. Electra, that is in Trieste, is a ring of lower energy than ESRF, that is in Grenoble, and one is in the sea, the other in the mountain. But both of them, they can do research in all the direction. They can do research on earth science, in material science. They can work on polymer science, biomimetic materials. Of course, develop research for energy and the environment. And last but not the least, research in biology, life science, and pharmaceutical research and development. Why synchroradiation as a neutron are so important for studying the structure of matter is easy seen if you look to the electromagnetic wavelength spectrum, and you see that the X-rays, they cover a range that is the range of the distance between atoms and molecules. So it's the best rule for measuring interatomic distances and looking which are the relation between the structure and the function of in materials. Of course, X-rays, they are known to everybody, have been invented a little bit more than 100 years ago. They are known because they are penetrating matter. That has been the first use in absolute, and is still one of the use that is normally known, from chest radiography to inspection like in the airport. If you look how inspection, the machine, the laboratory machine are done, they are not very different from the machine that were done, they were making X-rays years ago. That means a rotating anode. What you have is, see if I can have a pointer, you have a rotating disk, a target that rotates to dissipate somehow the energy that an electron beam is depositing on it. And when the electron beam hits the anode, there are fluorescence and Bremsstrahlung radiation that is emitted. This is the classic way of producing X-rays in this machine. Synchroradiation works in a different way. You have relativistic electron beam that are accelerated in a bending magnet, like here. You have a bending magnet, and you have a beam of electrons that goes through and emits a flash of radiation. Unfortunately, to do that is not, you cannot do it in a very small and compact way. You will see that there are attempts to reduce the dimension of X-ray source, but in general this is done in a big machine. This is a top view of the European Synchroradiation Facility. It's a circumference of about, the machine has a circumference 850 meters around, and if you open the top and you have a look, what you see is this. You have electrons that are emitted by a linear accelerator. They are accelerated in a synchrotron, and then finally they are injected on a storage ring, and anytime they go through magnetic element, they emit a flash of light. I think it's worth to remember how all this happened, who invented this, and I want to mention Bruno Tuschek, that has been a professor at the University of Rome, La Sapienza, in the 60s, and is the author of this sketch that we had the pleasure of seeing hanging up in the door of his auditorium class. And in the 60s, this elaborated a theory, the strong focusing theory, that made possible to convince the electron to stay together in a stable orbit and with very tight tolerance in a ring. And this is the first machine that has been built on this concept, was called ADA, anello di accumulazione. was a small machine of 1 meter. And since then, a number of development has been done. From ADA, the big brother that was Adone, that is still, the building is still in Frascati, down to the largest one, that the LHC in Switzerland, in Geneva, that is many tens of kilometers diameter. So these are 50 years of the transition between ADA to the LHC, are 50 years of story of development in machine physicists, a story in which the Italian physicist of machine had a very strong contribution. I close the parenthesis on how the radiation, how all that came up. And I remind you the main characteristic of synchoradiation: the brilliance, the coherence. Coherence is something that is extremely important nowadays, especially because if you have coherence, it means that you can do you use the phase to look at things instead of the intensity, and you can exploit effects that are important in biology as in many other areas. You have a pulsed emission, as you saw, and flux polarization, and of course an incredible beam stability, because the control on electron beam has reached a very high level of perfection. Now you can focus, here at the SRF, we can focus the X-ray beam to spot of 60, 70 nanometer with a very good stability. You keep the beam where it is. But the most striking characteristic is that you have 11 order of magnitude of brilliance higher than a standard source, and that lets you to do a number of experiments, not only, of course, the one that are using first order effect like transmission, but also the one that are second order effect like an elastic scattering, and other effects that are giving you information not only about the structure of the geometric structure of matter, but also photoemission give you information about the electronic structure of systems. The most known probably of all the technique is a crystallography. X-ray diffraction has been developed also about 100 years ago, and has given rise to a number of studies, has been probably the tool for learning and discovering what life is, and this is probably the reason why the structure of protein has the honor of being the first page of important, the main known review in science. Talking about publication, we can give some numbers about but this facility, which is the efficiency of these facilities, because eventually facilities, these machines, they are expensive, and of course they need to have a return on investment. We have at the SRF some few thousand, actually 7,000 visits of scientists every year. And the return is expressed in this number. They are not, this is for SRF, the other facilities are similar. They are not updated to 2014, but you see that the number of publications is a little bit less than 2,000 publications a year. And of these, the ones that are in high impact journals are around 200. But since it's an expensive machine, has to be, the cost is borne by a number of countries, at least for ESRF. I didn't at the time to redo the map, because there have been some changes lately. ESRF, I remade the change of this little rectangle this morning. There are 21 countries that are supporting ESRF, that is a Société Civile, under French laws. And there are a number of members, country, and associated. They are not anymore strictly European, because we have also South Africa, we have Israel, and of course, Italy has an important role with 15%, but 2 weeks ago, Russia joined as a member with a participation that will grow up to 6%. So it's a big machine. And in the afternoon, we'll see how you have access to this machine. If you make the sum of all these numbers, you see that the number is not 100, it's not 100%. Of course, there are some readjustment on the participation that has to be done in the future. Elettra has also a consortium, is a società senza fini di lucro di interesse nazionale, but the stockholders are all Italians in the case of Trieste. Now, a few words on what you can do with X-rays. Well, this is a big task, of course, so I will give some flash only few applications. One is trivial. You can look if a battery is charged or is not charged. You can say that it's much cheaper to do it with a voltmeter. It's true, but with voltmeter you don't know why it's charged or uncharged. With synchroradiation, with the tomography and with high-resolution tomography, you can see the status of the microscopic status of the single element of the battery, and that can help to make better batteries. This is, of course, a trivial experiment, but there are others that are having more important impact in energy. For example, the study of the coating, the tungsten coating on the stainless steel container of the tokamak for of ITER. Here, the stainless steel walls have been coated by a jet spray of tungsten, and then you want to know how the tungsten is well intrinsically mixed with the stainless steel. So you take a sample, you make microtomography, you can have a visual inspection of the steel, where it is, the tungsten, how it's distributed, and the pores that are left. And then from there you can make your statistic and see how to improve the coating process in order to have a better confinement cavity. But this is on material science. There are other types of material. Biomimetic materials are more and more important, and at the SRF, spiders are quite common. Historically, we start studying spiders, I think, 15 years ago, to know which is the structure of their silk that is much stronger of the best artificial fibers that men can fabricate, like Kevlar. So spiders are quite a good sample. You look to the structure with small angle scattering, and then you unveil their microscopic structure that actually is not so, is quite a complicated composite structure of amount crystals and linking agent. But there are other sciences that can profit of synchroradiation, and some of them they profit of the fact that you can focus the beam in very, very small spot size. It's in this way that you can study condition, recreate in laboratory condition that normally you cannot explore. For example, try to understand what's happening at the center of the Earth. That is not easy given the megabar, the many megabar of pressure and the many thousands of degrees of temperature. And that's is what is done with this cell that are called diagonal cell. And what makes this cell important is that inside you have two small diamonds. They are pressed together against your target, your material, the sample that you want to study through a gasket. And once you squeeze them together, you fire a powerful laser that is going through the diamond itself to heat it up. And in this way, you can reach pressure of few thousand of bar of pressure and few thousand of degrees of temperature, and study material in the same condition they are in the center of the Earth. Another area that is emerging more and more is the study of cultural heritage, just not only to reveal what is hidden behind a painting, but also how to understand how the chemistry is acting against the paintings or frescoes, and learn which is the best way to restore them. At synchrotron radiation here at the ESRF, we started we have a section of paleontology. Paleontology, before the development of synchron radiation, in order to study the structure of an archaeological object, was forced to make a slice of it. That means ruining forever. But now it's possible to use a not invasive technique to study this. And I make here an example for Sediba, that in a hominid species of 1.9 million years ago that has been discovered in South Africa, and is a poor family that fell down on a precipice and has been found only in 2008. And the images has been one of the school has been taken at ESRF for examination, and of course with synchron radiation you have a much better resolution than with laboratory machine. And what has been done a reconstruction, a tomographic reconstruction, and that is not only for seeing what you can do with a tomographic reconstruction, just to be able to formulate a model for the size of the brain and understand as possible reconstruct the way these our predecessors were living. I'm not going through what has been done in protein crystallography and in life science in general. During the day there will be other intervention, or that is clear that for the pharmaceutical industry, for life science, synchron radiation and protein crystallography is a must nowadays. I just finished giving a few numbers of what ESRF is and the LETRA are today. ESRF are 5,000 users. Some of them they come twice because they like the place or because they have a very good proposal accepted. So we have a total of 7,000 visits per year, and with a 2,000 proposal per year that compare well with almost 2,000 publications per year. We have 1,500 experimental sessions. The number of beamline is about 42. It's difficult to count the beamline because some of them they are split into publication. We said, of course, this machine they can operate only if there is a continuous technological development to keep them updated and up to the international level of science. We are now strongly involved in an upgrade. For example, we are extremely involved in an upgrade program that will last until 2019-2020, in which that will give the possibility to increase the brilliance of the beam of a factor from 50 to 100, then increasing the possibility of doing time-resolved experiment to exploit, to look in real time at what a chemical reaction is, to see to make a protein crystallography in real time, to make a movie out of it. Electra has similar numbers for Electra. There are 4,000 employees, 5,000 hours per year of beam time. So the two beam lines, 1,000 users, and users that are coming from more than 50 countries. With this, I finished my fast presentation of this facility, just to give an idea of how they work. So I thank you for your attention, and if you have a question, please.
Any questions? I don't see any questions, so I think we thank you again, and you will be connected anyway. So there is, if there are questions coming up later, you can answer later on.
Very good, thanks.
Okay, thank you. So we can move on to the next speaker, who is here, Robert McGreevy. He will tell us all about science at ILL and ISIS facility.
Okay, I have to stand here then.
Yeah.
Okay. Here it is.
Yes, okay. You can stand here and just.
Okay, thank you. It's a pleasure to be here in Milan. The weather is slightly better than England, but there you go. That's not unusual. So I'm going to give a short overview of neutron scattering, of the ISIS facility, and of the ILLs, cover that overall. Now, it was just interesting to me hearing Fabio Comin's talk, because one point that's not made a lot in my presentation, but I think we should stress, is the complementarity between these different techniques. And several of the examples that Fabio chose, for example, studying bits out of the interfusion source or spider silk, topics that are also studied using neutrons because they give you very complementary information about relatively complex problems. So the neutron was discovered in 1932 by James Chadwick. That's actually the little device he used to discover the neutrons. And interestingly, James Chadwick basically said that he didn't think they'd be rather interesting, but not very much use for anything. Fortunately, Enrico Fermi was slightly more foresighted, and his view was that all these technological developments eventually give you something that is actually extremely useful for society. And so, as I said, it's fortunate for us that he got that right, because there are multiple applications now of neutron scattering in many direct type, not just pure science studies, many science studies that have a lot of applications. I mean, I have said at various points that the neutrons are used to study everything from babies to bridges. Now, I don't actually mean that we study babies in the neutron beam, but for example, we've studied the problems of lung surfactants, what actually causes the premature baby lungs to collapse, and how you can treat, how you can put surfactants in the lungs that prevent that collapse, and so on. But also up to heavy engineering, actually studies of, for example, the twisted, what you call the cables that you use to support suspension bridges and so on. So, like the synchrotrons, an enormously wide range of applications. And particularly these days, I mean, so what Chadwick would have considered as the curiosity-driven research, the sort of stuff doesn't have direct applications. A very large amount of the applications nowadays are in areas like energy, health, digital economy, environment, and security, and so on, which are high-priority areas in pretty much all the countries in the world. So we're based at the Harwell site in Oxfordshire. This is a slightly old picture, but it rather nicely illustrates the fact that when neutron scattering started in the UK, this was one of the original research reactors. That's not quite that long ago, I'm not quite that old, but that's where I started my neutron scattering career. But at the same site, we had very early on both a reactor-driven source of neutrons and an accelerator-driven source of neutrons. So this facility here, eventually in the late 1970s, early 1980s, was one of the first accelerator-driven, it's actually an electron accelerator-driven source of neutrons on the same site. And so why neutrons? Okay, so neutrons obviously make half of the atomic nucleus. They are uncharged particles. That's one of the particular advantages of neutrons, that they do not have a charge, but they also have a magnetic moment. It actually happens that the amount of scattering you get from the nucleus from the Sorry, should I stand? I always feel when I'm standing behind one of these, like President Bush announcing that the war in Iraq is over. So, okay. So they're uncharged, but they also have a magnetic moment, and the scattering is about the same. So neutron scattering, for example, is one of the key techniques for studying magnetism at the atomic level. You can produce neutrons two ways. One is through beams of neutrons. One is through a nuclear reactor. So the Institute Lagrange in Grenoble has been essentially the highest flux source of neutrons for experiments since the 1970s. The particular issue is that this is about 200 megavolts produced in this reaction for 2.4 neutrons. You need to take about 1.4 of those neutrons to put back into the fission process to make it self-sustaining. So basically you get about 1 neutron for 200 megavolts. If you want to make a very bright source of neutrons, the problem is getting the heat out of the reactor. So that's why the ILL was essentially at the limit of its technology already in the 1970s. You can also use a spallation source, an accelerator-driven source of neutrons, is what we do at ISIS. It's a proton accelerator-driven source. And in this production case, we're producing about 20 megavolt per neutron. That's about an order of magnitude less, and therefore you have the opportunity to go to higher fluxes. These sources of neutrons are also pulse sources, so they produce a flash of neutrons, whereas the reactor are continuous. And again, depending on the experiment, you might want to use one or other. There are particular advantages either way. So the neutrons are uncharged. Their mass, or equivalent, their velocity is about 2 kilometers a second at room temperature, and their wavelength is about 0.2 nanometers. So the energy, both the energy and mass of the neutrons we are using are comparable to the energies of typical vibrations in molecules, for example, or to the typical spacings between atoms in molecules. So consequently, you can study at the atomic level, you can study both the structure and the dynamics relatively easily. If you just compared Fabio Camin's talk, so he was talking about the very high brightness sources of photons now are also being used to do inelastic scattering, but because there you're using kilovolt photons to study milli-electron volt excitations, that requires that much higher power source. In the neutron's case, studying inelastic scattering for excitations is actually an awful lot easier than it is with photons. So neutrons have been studying inelastic scattering excitations actually now for 40 or 50 years. So neutron wavelengths are the same order as atomic spacing, so we can get structural information over a very wide range of length scales, from the angstrom up to the micron, actually even larger than that. I mean, you can go up to macroscopic objects, as I said, like studying engineering objects, and a very high level of structural precision. That's extremely important. It's not only the range you can cover, but actually the precision you can get in that measurement. So neutrons are highly penetrating because they have no charge. That means you can study macroscopic objects. The movies here, I don't think are working. No, never mind. Okay. So this was actually a tomographic study of a statue. So the neutrons can penetrate through this metallic object and actually look at what's in the structure inside. This is one of my favorite examples. So this is actually a fossil containing the leaves of a monkey puzzle tree. So that's actually a rock. But with the neutrons, because you're penetrating the rock, but you're seeing essentially the hydrogen atoms inside that rock, you can actually pick out that fossil. That came from Antarctica when we had real global warming, and Antarctica was actually tropical. Somebody asked the question, how do you actually know there was a fossil inside the rock in the first place? Well, actually, you can see it on the surface, so they knew where to look. But the principle is this is non-destructive, so you don't actually need to cut these objects up to look inside of them. And again, neutrons will give you a different picture from the X-rays. So X-rays, here again is the typical picture for X-rays, where you're seeing, for example, the metallic object here, because X-rays scatter with the number of electrons in the atom, so the scattering goes up as the number of electrons increases. The neutron scattering varies in a fairly random way through the periodic table. So consequently, for example, you can see hydrogen quite easily, and so you can study light elements inside heavy elements. So in a sense, it gives you the opposite picture to what X-rays do. So if you looked at the body of this camera here, what you'd see with X-rays would be the metallic body of the camera, but in the case of neutrons, you can see the plastic components that are inside. And so again, very, very complementary techniques. A particular property of neutron scattering is that because it scatters from the nucleus, then the scattering from different isotopes of the same chemical element vary very considerably. So for example, hydrogen and deuterium have a very different scattering cross-section for neutrons. And that's extremely valuable because if you take the same molecule, for example, and you change particular bits of it for hydrogen or deuterium, you can change the scattering from a particular bit of a particular molecule. And that means you can take a complicated system, but it says here, the chemistry remains the same. I mean, that's not always true, actually. Very occasionally, it's slightly different. But in general, the chemistry remains the same. So I can take a complicated system, I can make a number of different versions of it with different amounts of hydrogen or deuterium, and I can actually pick out of that particular bits of the structure. And so here's a little example. This was done at ILL. This is a particular enzyme where you're doing 3 different measurements of that enzyme put together with different hydrogen deuterium compositions, and you see different parts of the structure in each measurement, and then you put that together to get the whole picture. And so these are, as you see, in the whole picture, these bits are actually intertwined. They're not actually separate pieces in physically different places. They're actually different molecules in different parts of the system. So that's a very complicated system being studied from using 3 different measurements. And this technique allowing you to do this is essentially unique to neutrons. There isn't another technique where you can unravel things, particularly widely used in biological applications or soft matter applications. And so Vicky Garcia-Sakai will talk this afternoon more about that. So most of these experiments will use this technique. So neutrons can also be used to study the magnetic structure because neutrons have a magnetic moment but no charge, particular advantage. So again, it's one of the fundamental techniques for studying magnetism. The other advantage of having a charge is you can actually polarize the neutron beam. And so by studying neutrons of different polarizations interacting with the magnetic system, you can actually much more cleanly separate out the magnetic scattering from the atomic scattering, which just for a straightforward neutron measurement, you can't do. The neutron itself is also studied, of course, because the neutron is a fundamental particle. So typical studies of neutrons include, for example, the electric dipole moment of the neutron, which is either 0 or extremely small, has been searched after for many, many years, and those searches get more and more precise. The lifetime of the neutron, so exactly how long does the neutron live, because it decays into a proton and an electron. It's about 15 minutes, but it's a very precise measurement. And these types of studies are actually done at the precision now where they are fundamental tests of things like the standard model of particle physics at a level which is comparable to what you can do with, of course, the very high energy accelerators like at CERN. So in some sense, they are actually competitive for studying those sort of fundamental questions. People would say they're an awful lot cheaper, actually, than running something like CERN, so there's always that argument. But essentially, these things are done at the normal neutron sources like ILL. At ISIS, we don't do them, but they do them at ILL. So this is the picture of the Rutherford-Appleton laboratory site, where we actually have both neutron source here. For example, ISIS produces neutrons and muons, which I'll mention in just a minute. We have the diamond synchrotron, which does the X-rays. In fact, we also have high-power laser facilities sitting just here. So there's lasers which overlap the applications of both ISIS and ILL. And also extremely importantly nowadays, but wasn't mentioned by Fabio, all of these sources produce vast amounts of data. Right? We are doing a lot of experiments. So like the tomographic images that Fabio showed of the skulls and so on. I mean, those imaging stations are producing enormous amounts of data all the time. So you also need on these sites high-performance computing. So our high-performance computing sits us there, for example. You've got to be able to handle all that and deal with it extremely quickly because the experiments get faster and faster. So for ISIS, typical statistics for ISIS, so we have, it's a slightly smaller scale of operation to say the ESRF, which is a very large scale operation. We have about 1,000 unique users per year, about 3,000 visiting scientists. We're producing about 450 publications, doing about 700 experiments. Although ISIS is a national facility, we have a significant amount of international use. I suppose it's a bit like saying Electra had people from 50 countries. We probably have users from at least 30 or 40 countries. I'm not sure we've counted them all exactly. We're about 75% UK use, 25% international. Rather unusual in that we are a national facility with quite a large proportion of funding coming from international partnerships, including, for example, the partnership with Italy. Italy is our oldest partner, been with ISIS since 1986, and been continually a partner since then at about the 5% level. We have about 15% of our experiments have an industrial partner. That's something we worked on a lot in the last few years, has been increasing. And this is increasingly important, at least from a government point of view, for justifying the cost of these large facilities. So this is the layout of ISIS. We're a proton accelerator. We have 2 target stations, which have essentially, you can think of them, if you're familiar with in the synchrotrons, you have these different insertion devices, bending magnets, or which produce different wavelengths of photons. In the neutron case, we have different target stations here with different moderators, and those are a bit like having the different insertion devices. And so they're optimized for different wavelength energy bands, and therefore different types of studies, different types of instruments. So at ISIS, we have about 30 instruments operating at the moment. I think that's on the next slide. So we have a range of instruments to study both structure, so powder diffraction, liquid or glass diffraction, small angle scattering, reflectometry, imaging, and also inelastic scattering, so neutron spectrometers. And we also have muon spectrometers. So in the beam here, we produce also muons, which go to 2 sets of instruments here. Muons can be used in a very similar way to we use the neutrons for studying materials at the atomic scale. Again, the muon is magnetic, so we can get information on magnetism, and the muon also acts as an analog of an isotope of hydrogen. So if you want to study systems where you want to study the behavior of particular hydrogen atoms at very low concentration, then quite often muons are a really unique tool for doing that. So things like studying free radicals, for example, or the study of very low concentrations of hydrogen in semiconductors and their behavior there. So these are the 30 instruments we have operating at the moment at ISIS. So the whole range of different types of science, again, similar to the synchrotrons. In our second target station, at the moment, we're building 4 new instruments, which include imaging. We don't have an imaging instrument at the moment. And an instrument for using neutrons for irradiation, which is high energy neutrons. And Giuseppe will talk about that later on today. In Grenoble, this is the European Photon and Neutron Science Campus. So you've just heard the talk about ESRF, and then you have the ILL sitting here producing the neutrons. So again, a very similar sort of site with the complementarity of the techniques. ILL is a slightly larger scale operation to ISIS, but it's very similar in many ways. So roughly 1,500 users per year, 1,400 proposals, 850 experiments, and so on. It's now running 28 public instruments, what we call public instruments, and 9 collaborating research groups, which are instruments which are partly public and also partly sort of privately run by those particular groups. In terms of the breakdown of the sorts of science that are done, then here you have, for example, health applications really quite large here, energy applications. I think that this is now up to about 12%, fundamental science, the broad area of material science, and so on. And that's really quite similar across these types of facilities. You'd find in the synchrotrons, the health and the biology area is somewhat larger, particularly because you have the very large area of protein crystallography. But in terms of the other instruments, the breakdown of the sorts of science that's done is actually really quite similar between neutron and photon sources. For the Italian participation in ISIS, as I said, this has been going on since 1985, and it includes 2 things. One is the Italian use of the facility, but also it's a very strong involvement in instrumentation and technique development. So through all these different agreements, we have particular areas of development that get focused on at each particular time. And I think that's extremely important if a country is going to be good at using these sort of techniques, these large facility techniques. You can't really just turn up. You have to have some level of expertise in understanding what those techniques can do well. And that has to, that's one of the roles of these sort of roadshows is to spread that knowledge out. So not only can you learn about the sort of things that can be done, but also you can make contact with people within your own country who have the expertise to help you out in making effective use of that. Otherwise you can use it, but you aren't not so often so really effective. So we have 300 Italian users on our database, lots of publications, lots of beam time being used. This was the breakdown from here. The cultural heritage side, it being Italy, is quite strong compared to, say, Britain, where we don't have the equivalent sort of cultural heritage, so we don't use that so much. And examples of collaborations in particular instruments. So this was one of the instruments on Target Station 2, the very large detector tank being built here, and instruments such as electron volt scattering. Italy has a CRG instrument at ISIS, which is called INIS, and Antonella is Chiarello is the instrument scientist on INIS. So a lot of different applications. Ancient Charm, which Giuseppe led, was an EU-funded project developing techniques in cultural heritage. So a wide range of activities, including now in our TS2 phase 2, that's our new instruments being built. And as I said, Giuseppe is going to talk about chip irradiation a bit later on. In terms of muons, so muons we use as for studying condensed matter in the same way. Actually, muons has equally had a very long Italian involvement. We call our muon facility the EC muon facility because it was originally funded by the EU Framework Programme 1. So that tells you how old that was. And Roberto De Renzi was actually one of the very original people who participated in that project and has been involved in the muons ever since the startup. So quite a broad Italian use, both of the neutrons and of the muons. At ILL, it's very similar. So Italy joined ILL, participated in ILL a long time ago. It's about a 5% partner, so that's roughly the same percentage as it is with ISIS. It runs 2 CRG instruments at ILL. One is BRISP, that's the instrument here, for Brillouin scattering, that's low energy inelastic scattering. And iron 13, which is also an inelastic scattering instrument for studying sort of quasi-elastic scattering studies of, say, biomolecules and so on. An extremely productive instrument here. And possibly Vicky's mentioning iron 13 later on. So in terms of the scientific applications of neutrons, there's no clock here, is there? Is there a clock? No. Okay, anyway. So I said, very broad range of scientific applications of neutrons. I'm just going to whiz through a few. I'm not going to talk about soft matter and biology because Vicky's talking about that later. Here's a nice example. So I said magnetism. Neutrons are very good at looking at magnetism. Molecular nanomagnets. So this is a collaboration with the University of Parma. Use both ISIS and ILL for doing structural studies. So this is the sort of magnet that's being looked at, quite complicated molecules. These are interest, for example, for quantum computing applications. So can you actually set the magnetic state of a particular magnetic atom on this ring and change it in relation to others? So you'll have structural studies of this to work out actually what is the magnetic structure of those systems. They've got quite complicated energy diagrams and here, but also tour de force inelastic scattering experiments. So this is an example. So once upon a time, if you did inelastic neutron scattering, then you needed samples that were basically several cubic centimeters of sample. These tiny little crystals put in here are sub-millimeter crystals, and you put them together on an array there to make something that's slightly larger volume, but is still a very small amount of material. But this is probably now state of the art in terms of what you can do with inelastic scattering from single crystals in this sort of study on a neutron source. It's really less than about a cubic millimeter of material in total there, which I said, go back 10 years, people would have told you that was impossible. And nowadays, with improved instrumentation, it's 500 tiny crystals being aligned there. As was previously mentioned, again, studying archaeological objects. So not only can you study that from an imaging point of view, so do tomography on that, but actually what you would do is study the metallurgy of these objects. So by using neutron diffraction, using texture measurements, you'd actually look at different parts of this and actually be able to work out not only what is the material that's in that, but also some indication of how that was actually made. Now, sometimes that allows you to actually say whether an object is a real object, so to speak, or not real object. So in some cases, we've been able to show that, for example, out of a set of coins, then these ones are originals, these ones are fakes, and so on. So you can use it for that sort of investigation. The same sort of techniques can be applied to both archaeology, but also to less interesting but more up-to-date problems. For example, just to study welding. So this is a part of a pipeline that will be used for oil, part of an oil pipeline, and the people here are studying the welds in that pipeline down the middle section to be looking at the stress in that weld. So we can study, so that's a complete object that would be studied in the neutron beam, and because the neutrons can penetrate those materials very easily, we can take something that's this large and, as I said, non-destructively study it. And that's not quite the largest thing that's ever been studied, but that's quite large. That's something that's of direct interest to industry. And again, it's the same technique that's being used to study both those modern problems and the cultural heritage problems. Similar ones in aerospace. So again, this is just another example. This is that's some part of a jet engine being shown there. Again, looking at the welding processes and so on. Okay. Other industry-related, so there's quite a lot of industry-related examples here. So studying graphite, so the UK has as many aging nuclear reactors. Then the graphite in these reactors is after some, I'm not quite sure what that picture is actually supposed to be. Yeah, that must be so those are the fuel elements. I'm not quite sure what the graphite is. But anyway, the graphite is starting to age. It starts to have, because of the radiation damage, it has small cracks and so on. And the companies need to know actually, what effect does that cracking have on the structural integrity of those components? And again, you can use neutrons to actually look at that non-destructively. You can actually take parts of that out and study it directly. In that particular case, we haven't managed to come up with anything that says these can have a longer lifetime, so they'll have to shut them down early anyway. In another particular case, where we were looking at welds in part of the cooling systems of advanced gas-cooled reactors, we have been able to demonstrate that actually these reactors could be relifed for another 5 years. So although in one case, if you like, for the industry, the answer was no, in the other case, this yes answer, that was actually preferable, somebody costed the value of that. The value of that is something like £5 billion. Okay, so that's an interesting, they didn't pay us £5 billion to do the study, but actually as a value, and that's one illustration we always have, is that people say, why don't you do more and more of this stuff for industry? Well, the answer is that what industry wants to do, sometimes the answer is yes and sometimes it's no. And actually more often than not, the answer is no, you can't do this, we can't solve that problem. But when it's yes, the answer may be something that's really, really valuable. Okay, let's get, these are similar examples. Giuseppe will talk about this later, so I'll just skip through that. Classic sort of uses of neutron scattering, say magnetism and high temperature superconductivity. So these are just pictures that come from inelastic scattering studies of the type that can be done nowadays. In the old days with neutron scattering, you take problems like this and essentially you'll be studying this one point at a time. You'll be working through it one single point at a time. Nowadays we can measure massive three-dimensional data sets and so get much more in-depth information about what are really, really complex problems. In this particular case, we have to make this up out of now quite large arrays of crystals being put together. But these really are forming much of the most important information about things like high temperature superconductivity. Now, when there is a Nobel Prize for explaining the origin of high temperature superconductivity, I can guarantee you two things. One is it will not be given to a neutron scatterer. It will be given to a theoretician who explains the data. But the other will be that the neutron scattering data will actually be at the core of what it takes to explain high temperature superconductivity. Because really it's the only way of looking in depth at that interaction between magnetism and superconductivity in such complex systems. And I think, probably, okay, then we have other examples. So actually studying quantum effects, so by using the higher energy end of neutrons, so we're using now electron volt neutrons. So we can use neutrons all the way between sub-millivolt and electron volt, a very wide range of neutron wavelengths. So by using the higher energy end, we can study things at the quantum level in molecules. So water has been studied with water, and every single form of water is one of the main areas of study with neutrons over very, very many years. And this is a particular example where you're studying it actually, how does the hydrogen behave in water at the quantum level. In terms of magnetism, again, here's another magnetism example, although it doesn't have the relevant picture here. So this is copper, manganese, arsenic. This was another example just to show nowadays how small materials you can study with neutrons. It was originally thought that you can only study, as I said, cubic centimeters or at best cubic millimeters of material with neutrons. This was actually sub-microgram amount of material. So with the brightness of instruments we have now and with the excellent signal to noise, this was actually a single crystal which was nanometers thick. Okay, so it's a really small amount of material. As I said, that's very different from what people in the past thought you could study with neutrons. Muons, muons are used in a very similar way. So we're using them to study, again, battery materials. So previously there was a picture from Fabio of imaging on a battery. Energy materials are a really large part of what's studied with neutrons, both particularly ones that contain hydrogen, but also contain light atoms like lithium, which are, so in say, lithium iron phosphate. It's relatively easy to see the lithium relative to, for example, the iron with neutrons, but you can also use these with lithium because the hydrogen will the muon will implant itself at a particular point in the material and give you information about the local environment around that as you're, for example, changing the properties of the material. So that was a very brief oversight, but at least I hope it's given you some idea of what RL analysis do, the very wide range of applications, and you'll get a sort of more in-depth view of different ones of those later on today. So, thank you.
Thank you, Robert. We can have questions to Robert, and then we have a short session of questions and answers. So first, is there any question on Robert's presentation? I don't see any. Well, the field is fascinating, but we can. I think maybe you can sit down and we see if we have done more general questions on this first part. So generally questions on these facilities. This is the first opportunity, and then we will have, after the coffee break, we will have a focus session, which has 6 presentations, and so there will be fewer opportunities for questions, but then there will be, after lunch, towards the end, there will be a session on access procedures, so how to apply for a beam time and this type of organizational matters. So I would leave that to later, but if there are general questions now on the use of these synchrotrons, yes.
Okay, that will not be a question, it will be a compliment for what has been told up to now about the role of CNR in these facilities, and in particular for what concerns Grenoble and Elettra. CNR manages all the CRG experiments in Grenoble, that means 2 CRGs mentioned before on the neutrons, and 1 CRG on the ESRF ring. And then out of the 32 beamlines that are present at Elettra, 9 of them are run by CNR. So this gives you the measure of how deeply is involved CNR in the activity on the larger scale facilities.
Thank you.
Well, I mean, as I indicated in my talk, I mean, CNR has been a wonderful partner for us. I mean, it's nearly 30 years now. Highly reliable. So that's one good point.
for such a question. I'm a biologist and I work with proteins. So my main usage of facilities is visiting synchrotrons. Nevertheless, I understand from your talk and other comments on the subject that there's a huge potentiality from neutron sources as well. I wonder whether you could comment or elaborate, or if this is more suitable for the later discussion, on what can be done on membrane proteins and the possibility of cancelling the contribution, say, of lipids or detergents by scattering in solution with neutrons.
Okay, so I'm not a biologist, so I have to be a little bit careful here in terms of. So you're asking a very specific question about membrane proteins, and maybe Vicky can answer that better. But I mean, just in general terms, in terms of neutrons, say, versus synchrotrons. So I mean, for protein crystallography, for example, neutrons, while they can do unique things in particular materials, will only ever be a tiny corner of that market, right? And that's partly because of the brightness of sources. You know, it was indicated like 11 orders of magnitude increase so with the synchrotrons, you can do entirely different things. With neutrons, you would have to study a very selected number of those problems, and therefore you pick out those ones where you say the neutrons can, in a particular case, make a difference, because you want to look at, say, the particular hydrogen atoms, ones that, for example, delocalized is typically done. Just in terms of the, actually for ISIS, for example, we don't do protein crystallography at the moment. Now, I was just to say, yeah, okay, so for solution studies, this is completely different. So in terms of small angle scattering studies, for example, in solution, or using neutron reflectometry, so a lot of the studies of membranes are actually done using reflectometry nowadays. This is where the ability to do the isotopic contrast is extremely valuable in picking out different parts of those things. So you have cases where, in some cases, you will actually try and produce lipids which are preferentially deuterated. So if you have a particular problem, you want to pick something out, you know, that's quite a large amount of work in itself. So the trick is all in the chemistry, or the biochemistry, if you like, rather than in the measurement. You've got to be able to produce the materials with the right hydrogen deuterium compositions to solve those problems. So whether a particular problem is doable or not actually depends on the biochemistry more than it does on the neutron technique end of it. But again, we would typically be using both X-rays and neutrons for many of these problems, because we always say that the X-ray is like doing an extra contrast. It's like the X-rays are equivalent of a different hydrogen deuterium composition. So you'd often do an X-ray study in, say, small angle scattering, and then do several neutron studies with different compositions of the material. But Vicky might want to.
Yeah, I mean, I'll give more examples at 2:30, which hopefully will become clear. But I think one thing is that for membrane proteins in particular, I think neutrons are extremely valuable because, you know, it's difficult to crystallize them. So the protein crystallography with X-rays would be hard. And in the membrane protein, you put it in your, you know, in the membrane itself and do the solution scattering with neutrons. You might not get the structural precision of every atomic position with the neutrons, but at least you can get a conformational state on how it binds to the membrane or sits within the membrane in terms of, you know, shape, like if it's standing upwards or lying flat on the surface, or which bit can stick in and bind to the inside of the membrane. If you can do the biochemistry, of course, and deuterate maybe bits of your protein and lipid. But yeah, it will be done in solution. And I think that's one of the key advantages of doing the neutrons for membrane proteins in particular.
About that, you have, I think, also in ISIS, there's the deuteration labs to help people to do the right deuteration of proteins membrane and everything like this. And in particular in ILL, there is an Italian person that's really expert in that, Giovanna Fragneto. So if you want to contact somebody, she is the perfect person to help you.
Yeah, I mean certainly for some of the lipids, for example, there are now regularly used methods of deuteration, etc. Again, as always with any of these things, the first thing you do is you pick up the phone and you ring the relevant person, and they'll tell you immediately what the answer is. Yeah, don't ring me because I don't know anything.
When I ring you to know whom I have to ring. Thank you.
Okay, yeah, that's true.
Right. Any other question of a general kind? We still have a couple of minutes, or we can slowly close the session and move to coffee. So, last call for questions? No more questions? Okay. Then we will have more time over coffee if there are questions to the various speakers. So, thanks again, and we'll get back. I should ask all speakers to load the presentations on the computer here during the coffee break, since we have a slow computer. It's better to do it before. So we get back here at 11:30.
So I think we should get started since we have now a number of short focus talks, presentations. So we have 6. The one in video conference from Grenoble, given by Alberto Bravin, will be at the end of the session. So it will be the last one, and the rest of the program should be as is, as you see on the printout. So, and each speaker has 15 minutes, including questions. So I would like to call the first speaker, Beatrice. There you are. Beatrice Vallone. She will tell us all about the biocrystal facility at the CNR IBPM.
Hello, thank you for inviting me. And I will give you, I would say, part of the users side of the applications and potentialities of large facilities such as the ESRF, ELECTRA, ELL, and ISIS for research projects in structural biology mainly. So my name is Beatrice Vallone. I work at the Department of Biochemistry of the Sapienza University in Rome, and I am also associated to the CNR Institute. Now then, just a brief overview of structural biology and questions and answers coming from this methodology. And of course, we do heavily rely on synchrotron sources for our experimental activities. Now then, so X-ray crystallography enables us to visualize not just protein structures, but more widely speaking, biological macromolecules. And it enhances our understanding of function because we do manage actually to see what happens at the molecular level in living organisms. And we do also analyze dynamics and interactions between different macromolecules and smaller elements such as substrates, inhibitors, and messengers, and so on. So just a brief survey of our results. We are focused also on drug design, vaccines, and of course this is not our work, but from the ribosome structure, which was mentioned also by Fabio earlier on, you may understand how tiny molecules such as antibiotics, which are currently used in therapy of infectious diseases, do block protein synthesis in bacteria and therefore design or even improve pre-existing molecules. And this is a reason of pride even for non-Nobel Prize winners, crystallographers, that actually this is protein crystallography, X-ray crystallography in general, has been one of the methodologies that yielded the richest harvest of Nobel Prizes in the last decades. The Protein Data Bank, which is a global database where protein structures are deposited once they are determined with different techniques, mainly X-ray crystallography, but also NMR and electron microscopy, and also modeling actually, has been growing basically also due to the availability of synchrotron sources, but not only, also biotech had its share in this rapid increase of the deposition and therefore our knowledge of the molecular activities of cells to understand physiology, pathology, and to, of course, also to several pharmaceutical applications. Actually, just a few months ago, we got 100,000 depositions in the PDB. In our group, we focus, in our laboratory actually, including my group, we focus on curiosity-driven research and also applied research, molecular oncology, drug targets, and also protein dynamics by utilizing a wide gamut of methodologies and synchrotrons, from classic diffraction to time-resolved X-ray diffraction. And here are some results. We work on nanotechnology. We engineer protein for therapy and diagnostics. This is a work carried out by Dr. Ilari at the CNR, working on a ferritin that has been engineered for actually diagnostics and also therapy in cancer, in oncology. I will go as fast as possible because I want to focus on what I do believe is more interesting for you than our results. We also did some patents, especially in this case. This is antibiotics again. We improved, based on protein crystallography, one enzyme in order to increase the biosynthetic industrial fermentation for producing erythromycin. Now then, and we also work in molecular oncology, of course. So what is hopefully my contribution to you convening here to learn about large facilities and research? As a user, of course, I am, and as a user since several years, I'm one of the advocates of the fundamental resource that is available to us within these facilities. We have the possibility of carrying out research, and we have the support not just for data collection, but also for technical advice and developments, as it was also underlined by the previous speakers at these facilities. And as we will see later, scientists, fellow scientists working at facilities are very helpful, very knowledgeable, and willing to help us design experiments and devices for us to produce successful science and experiments. And of course, as users, have to do our share. And in this time of hardship that we are all facing these days, never mind, something happened here. Okay, that's it. At one point, we tried to short-circuit what our experience was with the CNR and the university, and try to act as a, what can I say, to stimulate and to support our colleagues who not yet have accessed facilities to be a connection, another connection for Italian scientists to take the advantage of this opportunity. And our contribution was basically to put our instruments and our knowledge and make it available to the wider Italian community in the field. And the idea was basically, something is not working actually. Okay, lovely. So we have, with the support, the brief support, I have to say, of the CNR, created the so-called, what we pompously call biocrystal facility in our institute and department. And basically, our purpose was to facilitate and increase the use of the European synchrotron radiation facilities by the Italian scientific community. So we also collaborate with the SRF. There was recently a signed agreement for usage of the PSB, the Partnership for Structural Biology, from the CNR and Italian scientists, which we have to some extent nurtured. And basically what happens is that imagine you are a molecular biologist and you have a protein. You want to know the structure, and you think that you cannot do crystallography because it's as it was when I started, but no, I mean, it's not like that anymore, luckily. The crystallographers were a different breed, living at some in some limbo in between chemistry, physics, and biology. And what they did was mysterious, and at one point they would come up with the structure. Now, the methodology, thanks to synchrotron, increases and improvements in the computational suites and so on, available to a much wider audience. So basically, you, molecular biologists, if there's any in the audience, come to us and say, I have this protein, I have this gene, I have this problem. And I believe that the structure would answer some of my questions. We would talk together about it and see whether your project is feasible. So is your protein stable enough? If it's denatured or natively unfolded, we would direct you to SACS people or SANS people, or we would say, yes, you can crystallize it. So we do give our suggestions and support on the production and purification of proteins, and once you have your protein, you can send it to us, ship it to us, or bring it to us, and we would crystallize it, try to crystallize it, and go from these tiny crystals to those beautiful crystals. This would be also if you are a crystallographer and you don't have a robot in your lab, because it's quite an expensive piece of equipment and rather expensive to maintain, actually. Then, but if you actually would rather like to, we would go and collect data for you at ESRF or ELECTRA, DESI, wherever we have time. We have open application in a number of European synchrotrons, and we could train your student or your PhD or your graduate student or your research staff scientist, if he wants to come to us for a while, refine, determine, refine, and give you the structure. And then you can do whatever you want with it, publish it, at least. And this is accessed by the web. There's a website of our facility. You just send a mail to me or to other staff in the facility, or to even give us a ring, and we will decide and try to support you as much as possible, even if you just want to write an application for a large facility of this type. And there's a scientific committee which is checking your project, and I mean, most likely you will become one of our users. Actually, the last development, of which I'm really proud, is the facility within the facility. That is that there are many advantages, of course, and I'm a great advocate to ESRF, ILL, this type of labs. But they, on top of giving you support for that specific experiment, they are also an aggregation point for other facilities that support you in running your experiments. Protein production, protein characterization, other labs for material science, which I'm not at all knowledgeable, so I'd rather not mention that, but I know that there's also a partnership for material science running now, being set up in ESRF. We took the advantage of the support of the Oxford Protein Production Factory at Harwell and of the Instruct project to nurture the development, the establishment of a protein production factory in Italy, which is going to be operational since September, which is located in a research institute in Avellino, close to Avellino, in between Avellino and Benevento, actually, where you can also have your protein produced at a relatively low cost at this point, because there is no actual support for that from either CNR or universities. And I wish to thank actually the OPPF for the training and Instruct for support we got from them. Okay, our equipment, our robot, these are the microplates which are used for protein crystallization, and we don't use an anode, rotating anode anymore. We only go to synchrotrons, and this is our people. At the synchrotrons, it can become quite wild at some points, or you have, I mean, relatively more quiet moment in which you can take a nap And in the end, you have your crystals and eventually your structure. And I'm ready for questions, if there are any, of course.
Yeah.
Any questions from the audience? So this is...
There's a question from the audience.
There is, yes.
So how do you see the role, so you're providing a support facility, for example, and the synchrotron is also providing a support facility, and there's hundreds of different studies going through these facilities. How do you see the role of the scientists who are working at the support facilities now compared to those who are, if you like, doing the research? And because you still need highly qualified scientists to do this sort of work, but they're seeing all the other people coming through and getting the Nobel Prizes and things, and they're just running the machines.
This is, you are raising a point, a very crucial point. That is that scientists who work at synchrotrons should get more recognition for the work they carry out, or facilities. Of course, that includes neutron facilities as well. I think that from protein crystallography, the thing has degenerated a bit. That is that beamline scientists have such a large flow of users that in most cases it's quite difficult for them to see their work acknowledged. On the other hand, for long-term projects where you don't just go and collect data there, definitely the contribution is fundamental. But I think that a solution has to be found, either, which is what is done in some synchrotrons where scientists still do carry out their projects, and that should be encouraged in collaboration. For example, the OPPF is, I think as far as I know, they have some projects on their own on glycosylated proteins, and they do the science. So I think that scientists working at facilities must be allowed and encouraged to have research projects in collaboration and have a scientific productivity to some extent. Otherwise, they would just, get seedy and lost contact. So on one side, I think that there should be some room left, that scientists working at facilities must not be forced to work for users only. But on the other hand, even if they worked only for the users, they're still doing science. So as a scientist who's still working in a university or research institute, I think that people working at facilities are doing science, and they absolutely must not be regarded simply as people providing a service. That is wrong. And I'm an advocate for that, even if, I don't work at a facility, so but I see the crucial point, at least in my research field, for having real scientists doing the job. I hope that I answer your question.
Okay. So unless there is another quick question, no, then we thank Beatrice again, and we move on to the next talk, which is given by Luca Serafini.
Questo è il result point?
Sì.
Quello andato avanti?
Ricette, se vuoi spostarti.
Sì. Ma forse
va bene, quindi se stai in piedi qui.
Sì, sto in piedi qua. Perfetto. Poi sai che io ho una voce abbastanza.
Non trovo.
Dovrebbe essere questo. Questa.
Ecco qua. No, sta nulla. Ha sempre qualcosa da dire. Ecco.
So the talk is on the physics and perspectives of Thomson-Compton sources.
Thank you, Mr. Chairman. So today I will give you an overview of this new emerging technology based on backscattering Thomson sources of X-ray and gamma rays. And I will try to illustrate how this emerging technology is aiming at providing to the scientific community a new probe for investigating matter at the atomic level and also at the nuclear level. So for doing so, I will give you a brief overview of the physics of these electron-photon backscattering sources, and I will try to illustrate how these sources are small colliders, and I will try to show you that it's a rapidly growing field, strongly application-driven, and the appealing characteristic of these radiation sources is their compactness and low cost compared to the big infrastructure machine that we are talking about in this meeting. Also, I will try to show you what are the similarities in terms of the physics and technology of these compact sources to synchrotron light sources and free electron laser. And also I will try to underline the peculiarities, both in terms of the technology enabled and in terms of the performances. I'm quite sorry to say that in Europe we are sort of following the US and Japan in pursuing this emerging technology, and especially in the low energy range, compact Thomson sources of X-rays. We have now a couple or a few sources in construction in Europe, namely Spark Lab in Frascati, Tomex in Paris, STAR at Unical in Cosenza, and ELBE in Germany. But we have also in the nuclear photonic range, so in the MEV, gamma ray energy range, we have an ongoing project in Romania, in Bucharest, in the frame of the E-Lion pillar, which is the so-called gamma beam system, aimed at upgrading the present state-of-the-art in monochromatic gamma ray beam production by a few orders of magnitude. So this is an advanced project which will put Europe at the leadership in the development of this kind of machines. So the similarity is quite obvious. In a free electron laser or in a synchrotron light source, we launch a relativistic electron beam through a magnetostatic undulator, and we produce by undulator radiation monochromatic high brilliance X-ray beam. In the same way, in a compact Thomson source, we use a small photoinjector, a small LINAC, with tens of MeV or 100 of MeV electron beam, and we launch the electron beam through a laser pulse, an optical counter-propagating laser pulse. And we can imagine that this laser pulse is acting in the same way as the undulator radiation. So it is making the electron beam wiggling and producing dipole radiation, which follows strictly the electron beam propagation axis. And in fact, we can derive a quite simple relationship linking the radiation wavelength produced as a function of the laser wavelength, and we have this Lorentz boosting factor 1 over gamma square, which resembles in all ways the relationship for the free electron laser or the spontaneous undulator radiation. And as you can see, to produce 1 angstrom X-rays, you need multi-GeV electron beam, in this case, while you need a quite low energy electron beam in the case of Thomson X-ray sources. Unfortunately, this is only a part of the story when you look at the Thomson or Compton sources. In fact, you can easily see that if you increase the electron beam energy, the wavelength of the radiation can go down indefinitely to very small numbers. That means that at some point you are going to violate the energy conservation. The energy of the scattered photon can be higher than the energy of the incoming electron, which is clearly wrong. So when you have to design this Compton backscattering source, you have also to take care about a quantum view of the scattering between the two particles, the electron and the laser photons, scattering into a scattered electron and a scattered high energy gamma or X-ray photons. And if you do everything properly, assuming conservation of energy and momentum, you come out with a more complete view. And this view of the energy of the scattered X-ray or gamma ray photons as a function of the energy of the incoming electron, taking into account the scattering of a visible light, sort of a green light photons carried by the incoming laser pulse, you see that in this plot, if you look at free electron laser or synchrotron light sources, they follow the pure gamma square line. So for multi-GV or even a TV incoming electron energy, you would produce hundreds of keV or tens of MeV photons in a pure elastic scattering mode. But when you are scattering visible photons instead of virtual photons, centimeter wavelength long of the undulator equivalent virtual photon, then you have to take care about energy conservation. And in fact, you see that if you use up to a few hundred of MeV incoming electrons, you are in the elastic Thomson X-ray region in which you produce photons up to a few hundreds of keV. And the relationship is perfectly linear or better, following the gamma square a boost of the scattered photon energy. But when you enter the nuclear photonics range, in which you start scattering, let's say, 1 GeV electrons of a visible laser photon, then you start to see that the energy of the photon departs from the elastic scattering prediction, and you start to have a recoil. So the recoil of the electron starts to give you an effect which is given by this formula, in which the first part is the elastic Thomson contribution, and this small factor delta, which is small for electron energies up to a few GeV, it represents a redshift of the radiation due to the recoil of the incoming electron. Of course, if you keep going and you go into the TV collider, gamma-gamma collider range, you are going into the deep Compton, deep recoil range, in which the conservation of energy and momentum starts playing an important role. It's important to notice that even in this range of nuclear photonics, although the redshift is small, it may be of the order of a few percent, it may be not negligible and important to be taken into account, because in this range you aim at producing a very narrow bandwidth radiation. The radiation for nuclear photonics typically of the order of less than 1% in bandwidth. So you have to take care of this recoil effect, otherwise your source may be not well designed. So in a nutshell, the physics of Compton-Thomson backscattering is quite straightforward and well known since a long time. But going from the knowledge of the physics to the challenge of designing a high luminosity collider providing a high spectral flux and a high quality X gamma ray beam is a completely different topic. And in fact, because we are going to collide two beams, we need the two beams high density matched in time and in space. And this has many requirements on the laser, colliding laser, and on the colliding electron part. So we will be talking about a few micron size collision spot size for both beams. We will be talking about picosecond long, so a few hundreds of micron long, either laser pulses or electron pulses, which immediately tells you that the collision is efficient only if you have a good time-space overlap between the two beams. And so we can, let's say, view and design these machines as if they were a linear collider. And in our machine physicists that design this machine are use this very well-known luminosity equation telling you that the number of events, the number of photons that you want is just this factor, this geometrical factor, which is the luminosity, times the cross-section. The cross-section is the standard Thomson or Compton Klein-Nishima cross-section, depending on the regime you are, and there is nothing much we can do about it. So in order to maximize the number of photons, we have to maximize the number of colliding particles in the two bunches and to minimize the cross-section at the collision. In many applications, we don't really care about the number of photons, but we care about the so-called spectral luminosity, number of photons divided the bandwidth. Especially in the nuclear photonics application, you want many photons per second, but you want these photons very concentrated in a narrow bandwidth. So we care about this spectral luminosity in which the bandwidth comes in. Another important aspect of these sources is that these sources are polychromatic. They are not intrinsically monochromatic. Here you see the spectrum of photons scattered up to 5 MeV. In this particular example, I'm using a 500 MeV electron beam against a green laser. And you see the distribution of scattered photons goes from 5 MeV down to 0. So in order to have a monochromatic source, I need to collimate and to intercept in a narrow solid angle only photons scattered in a collimated, a very narrow solid angle in the direction of propagation of the electron beam. And in doing that, I have to come out, this is an example for the ELINP machine, with very complex and sophisticated collimator that I have to select a few tenths of microradian of solid angle in the forward direction. So I will skip this part on the ELINP machine because probably Sandro De Silvestri will speak about that, and I want to show you an example of a compact X-ray Thomson source which is under construction at the University of Calabria in Cosenza. The name of the machine is START, for Southern Europe Thomson Source for Applied Research. It's quite a compact machine which is 10 meters long with a short radio frequency LINAC, producing electrons up to 70 MeV and X-ray photons up to 100 keV. This machine has been intelligently copied by the Spark Lab Thomson source. Spark Lab in Frascati is aimed to be a test facility while the STAR machine is aimed to become a user facility. And I can just show you the predicted performances. With 65 electron beam, we should be able to produce up to 70 kV X-rays with the fundamental of the laser, while scattering the second harmonic, we should go up to 180 kV. We have also the ambitious goal of increasing the energy of the LINAC. This is the peculiarity of these compact Thomson sources. You can easily, if you have the money and the resources, increase the energy of the electron beam, and in this way, if we can go up to 350 MeV, we can start working in the nuclear photonic range where we would be producing gamma ray beam at 1 MeV. For the time being, only this phase 1 is funded, so we will be able to go up to 160 kV with photons flux in this range. And okay, let me skip this part of the nuclear photonics. I want just to give you as a conclusion what are the peculiarities of these Compton X-ray Thomson sources with respect to the large facilities that we are talking about based on free electron laser or on synchrotron source. These are machines that can go up to the MeV class photon beams with reasonable size and modest costs. We are talking about 20 million euros instead of 200 or 600 million euros for a synchrotron. They have a control monochromaticity by collimation in this range of values. They intrinsically produce very short X-ray pulses from a few hundred femtosecond to a few picosecond. The fluxes expected are in this range of photons per second within this bandwidth. They have full control of linear polarization up to a very high level, and they can have a fast switching between two vertical and horizontal polarization, and this appears to be a very important aspect for the nuclear applications. And they come from round sources with round spot size down to a few micron spot size, which enable faint contrast enhancement due to the local coherence of the dye source. Okay, that's it. Thank you.
Time for a quick question. No quick question, but so you said that Spark Lab is for development, whereas in Cosenza you will have the...
Yes, actually at Spark Lab, I forgot to make some good propaganda here. We observed the very first X-ray photons in April, a couple months ago. So the Thomson X-ray source under construction in LNF and Spark Lab started its life very recently. And the purpose of this source is to characterize the collision and the emission process and to learn all the technological aspects, not only the production of the radiation, but also in the characterization and in the monitoring. It is aimed at some radiological imaging experiments, but by definition of Spark Lab, it cannot be a user facility because Spark Lab has a wide spectrum of scientific case going from advanced plasma acceleration to terahertz free electron laser, and so the Thomson source is just one experiment in there. While STAR in Cosenza has been funded to become a user facility, and we hope that in a couple of years since now we will be producing the first X-ray beam for the users.
Okay. Good luck. We all look forward to that. Thank you very much.
Thank you.
And the next Next speaker is Angelo Taibi from University of Ferrara. And he will tell us about it's more about monochromatic X-rays for advanced applications of diagnostic radiology.
Good morning, and thank you for this invitation. I'm a medical physicist, and I share the work with Mauro Gambaccini, who is the leader of our medical physics group. So, first of all, why monochromatic X-rays? If we look at this picture, we know that after 100 years of technological improvement, more than 100 years in X-ray imaging, we almost improved this detector side, which means that from screen film system we went to digital radiology. Now with flat panel we have a high efficiency detector with high resolution and are almost ideal for X-ray imaging. But on that X-ray side, we still rely on the X-ray tube, at least in the clinical context. Of course, we know that there are synchronous radiation now, Thomson sources, but in our clinical examination, we'll have to use this polychromatic X-ray beam. Polychromatic X-ray beam means that basically we have a Bremsstrahlung here with the characteristic X-ray line, and of course this is far from ideal because I'm stuck to them. What happens now? Ho spinto qualcosa che non dovevo.
No, non penso. Come è uscito lui
qua. Yes, okay, sorry. Beam hardening from the entrance spectrum to the exit spectrum. We see here for two particular cases that the lower part of the spectrum basically is those without signal. So what we would like to obtain is a monochromatic X-ray, so we only change the intensity. Of course, we have only one energy, which is suited for the particular application instead of this polychromatic source, and optimization in terms of dose and image quality, because we know that for each clinical examination there is an optimum X-ray energy which optimize, lower the dose and enhance the contrast or signal to noise ratio. We would like to use monochromatic with tunable feature, and of course in terms of diagnostic radiology it's very important to optimize this kind of X-ray source, especially because if we work in terms of dose, here at the bottom we have the statistics. So we want to get the same statistics with a conventional X-ray tube and quasi-monochromatic X-ray beam. Now I'm going to talk about the quasi-monochromatic X-ray beam. We know that to get the same statistics, we can get a much lower entrance dose. In this case, with respect to this case for chest radiography, the same plot for mammography, and we have for the same X-ray statistics, the signal to noise ratio at the detector level, we have very different numbers. So we can save those for screening program, and a lot of applications can benefit from the use of an X-ray monochromatic source, and this is a list of dose reduction for several examination type. Now, to get monochromatic X-ray beams, of course, we can start from synchronous radiation. We in Ferrara, we've been the first in the world to show monochromatic X-ray mammography, and now there are a lot of projects, Electra, ESRF, and all over the world for diagnostic radiology. But we would like to fill the gap, as we say, because in the clinical context we have to be, of course, low cost, compact, and tunable at the same time. So what we have done is to monochromatize X-rays from conventional X-ray tubes, but instead of using the pure black diffraction, because of course the flux is very low, we use a mosaic crystal, which means that we can enlarge the photon flux at the expenses of the monochromaticity. And the project that we have started many years ago from the mammography and synchronous radiation and the compact sources, and then we designed and built an X-ray prototype for clinical application. So this is the prototype, and the real thing is on this other figure. It's a scanning system, and we can see the monochromatic system here, the X-ray tube, and then the phantom at the bottom. Now we characterize, of course, the X-ray beam. We can tune our X-ray source in the mammography field. Now, in this particular case, we only have 10% of energy resolution and an exposure level which is enough for medical application. But on the other side, if we have a radiographic test with phantom and also with real breast, we know that there are problems in terms of X-ray and in terms of spatial resolution, because mammography, for example, or other applications are very challenging in terms of spatial resolution. So in this case, we lose resolution, and again, we have the problem to fill the gap with a photon source, which is very optimized in terms of X-ray flux, but at the same time with a small focal spot. So now, of course, I won't repeat this particular source. Now Ferrari is also involved in this big project, and we hope again to fill the gap from synchron radiation to more compact and suitable in a clinical context X-ray source. Now, just a little bit of rationale about the use of monochromatic X-rays, because if we only concentrate on those, of course, it's an important thing for a screening program, but the final goal is to use advanced application. Advanced means that now we want to extract for a better diagnosis a signal which is very tiny because of the structural noise and then image. And in fact, if we see here from the very first radiography and then computed radiography and digital radiology, we feel that through image processing we can get a better image. But as has been recognized already 30 years ago, if we don't produce image subtraction of what? Or what is the radiographic contrast of the healthy tissue, which is a complex background, we won't get any improvement in terms of signal to noise ratio. So again, we need multiple exposures, for example, and for this case, monochromatic source is very important. For example, here is for mammography. If we want to have a diagnosis on a fatty breast, means that the background of the healthy tissue is very flat, and the lesion here is apparent. But in this case of dense breast, which 25% of women belong to this category, here it's very difficult. So the challenge is how to look at this particular lesion. To do that, we have to subtract the structure noise, subtract in terms of depth, like CT scanning, or for dual energy application, or like the angiography with a mask, or via phase contrast. Phase contrast is another interesting application, and of course monochromatic radiation is the best choice, and here with synchron radiation we have already from electron studies our results. And another interesting thing is also that there are current applications with chest and bone mineral density that makes use of dual energy. Dual energy, a combination of a low energy and high energy image. And then, for example, we can separate two categories of tissue. Instead of having bone tissue and soft tissue here, we can separate and look only at one of this signal to better identify the lesion itself. And another thing which is very important for tumor angiogenesis, because if we want to subtract the structural noise, we can take advantage of this KH of iodine. We inject iodine, which is a contrast medium here, and via dual energy, if we have a monochromatic energy below and above the KH, we can subtract and only get the signal of this KH itself by cancelling the contrast of the healthy tissue. And if we look, for example, at a clinical application, which is here with mammographic unit, again with polychromatic X-ray sources and low and high energy, there are artifacts we are not able to completely subtract. So again, monochromatic with dual energy would be very interesting. Another interesting thing is also the spectral mammography, because breast density is another important parameter in breast imaging, and also to characterize the tissue which could be disease tissue. For example, here, if we have low and high energy, we can investigate and know exactly what kind of tissue is in a non-invasive way. The last application is like digital breast tomosynthesis, because of course we want to reconstruct the 3D tissue. And in this case, we need multiple exposures. So if we increase the dose, in this case, there are limitations for the clinical application. But in monochromatic X-rays, we can significantly lower the dose and do multiple applications to reconstruct and separate the tissue itself. Like, for example, in this case, this is an anthropomorphic phantom with certain details in the middle. And if we look at the mammography here, we don't see the masses, which is mimic the tumor itself. If we select a slice here in DBT, we can clearly see the details, and again, by a tissue separation, we can improve the image quality. So with DBT, it's like having a low angle cone beam CT. We can separate our planes, and the radiologist can scroll all the image in sequence. So in conclusion, which is of course a very fast presentation itself, we know that the fundamental limitation in diagnostic radiology is the so-called structure noise. It's not quantum noise, but it's the presence of the structure background, which could be very complex in the chest, in the breast, and so on. If we are able to introduce monochromatic rays, of course, we can boost this development of advanced application of medical imaging. And already shown by the previous speakers that there are innovative solutions, because we need to fill the gap. After all these years, we still, for diagnostic radiology, have the X-ray tube, and hopefully sooner or later we can get new sources. Thank you for your attention.
Thank you very much. As usual, we have time for a couple of questions. One question.
Just a curiosity, in the emission spectrum of the tungsten anode in your data, you showed 4 emission lines superimposed to the background. I can understand the 2 at highest energies, K alpha, K beta of tungsten, but I don't understand which are the other 2.
You mean at the beginning?
Yeah, just at the beginning. If you want already here. You see, you have a couple of lines above 60 kV, K alpha, K beta. What are the other 2 lines?
What the energy? I cannot read the energy myself. But
maybe there was another.
Yeah.
The previous picture of the energy was better. Okay. These 2 lines.
Yes, this 60 and 70.
Yeah.
Yes, it should be the case.
Well, K alpha, K beta should be those at above 60 kV.
Yes, at 60. And here at 70, I guess there are 2
yeah.
lines themselves.
And that's K alpha, K beta also for the amplitude ratio. But the other 2, what are?
This 2 here. Yeah, I cannot answer as well, because this was provided by someone, but I guess that there must be reason stems of characteristic lines of the spectrum itself, because it's 60 and 70. I will investigate as well.
So in analysing the images, is there any scope for what you might call learning? So in analysing images, there will be a percentage of patients who, for example, then have had surgery. So you know what the outcome was. Is there any process that goes through saying this was the outcome, this was the image? Can we have some learning process for learning from those outcomes? That this was, for example, a tumour, this wasn't? Or does that...
You mean for tissue characterization, in terms of, because often when you look at the lesion, of course it could be like false negative and false positive. So normally the radiologist has to perform biopsy. So the goal is to increase the sensitivity, let's say. On one side, sensitivity means that you can see the cancer at the early stage, and specificity, because of course you would like to know what is cancer and what is not. And the only way is by dual energy, because you can characterize exactly what kind of signal you get.
But how do you take the information that you get from biopsy and feed that back into the image analysis?
Sorry, I didn't...
Can you take the information you get from the biopsy and feed it back into the image analysis?
But you already performed the biopsy in this case. So the idea is to avoid the biopsy, of course.
Yeah, but can't you improve that by, if you've had lots of images,
yes,
and you've had lots of biopsies, and you know which ones were false and which ones are correct, can you now improve your image recognition using the information from the biopsy?
This is in fact CAD, computer-aided diagnosis. In fact, if you use this guy, but okay, this is another, let's say you learn from the statistics. Okay, yes, image processing, but in this case, for screening purposes, because screening means asymptomatic women that in principle have no history of cancers. So in this case, you would like to avoid the follow-up. I mean, only the mammography and immediately separate.
Okay, thank you. Thank the speaker again. Scusate, possiamo controllare la situazione a Grenoble? Vedere se c'è nessuno, se... Dobbiamo switchare.
Sì, siamo qui.
Ok.
Ci sentite?
Sì, tu senti noi?
Sì. Sì, va tutto bene. Allora, Alberto è qui.
Se volete manteniamo allora il programma come avevamo previsto e facciamo fare la vostra presentazione.
Sì, va bene.
Va bene?
Ok, cedo perfetto. Il controllo.
Quindi il prossimo speaker è Alberto Bravin e ci parla delle... next speaker is Alberto Bravin. Sorry, I had switched language. Biomedical science at the ESRF.
Hello, good morning. Can you hear me?
Yes, we can.
Okay.
Yes, we can hear you.
Okay, can you kindly switch to my presentation, to my computer?
I will do it.
1 second, we are doing that. Here we are. Okay, so good morning everyone, and thank you very much for the kind invitation. I will try to summarize in today's presentation which are the possibilities and the tools offered by the biomedical beamline at the European synchrotron here in Grenoble. So this is already the vision of the biomedical beamline. You can immediately realize that it's located outside the main ring. At least part of the beamline is located outside. There is the second experimental arch, which is located here. I don't know if you can follow my mouse. And then we have a biomedical facility, which is the second building, which includes ancillary laboratory to facilitate and permit yearly analysis of the samples or their preparation. So the beamline has two main experimental stations. One experimental station is located inside the ring, is a white beam station, is where we perform preclinical and clinical trials in microbeam radiation therapy. The second experimental station is instead located outside the ring, is the one that you have seen in the previous picture, and is allowed only for monochromatic X-rays, and they are applied for either preclinical imaging, high resolution, phase contrast, or dual energy imaging, and for a second radiation therapy program, where we already have recruited 6 patients and treated for phase 1, phase 2 clinical trials. So if we go more into the details of the beamline, I think you will realize that this is quite the ideal setup for a broad range of medical and biomedical applications. On the left side, you see the internal part, the characteristic of the internal part of the beamline. So we have a filtered X-ray beam ranging up to about 300 kiloelectron volts in filtered mode. We have a very high dose weight, I think the highest possible and available at the synchrotron facility on a wide field of about 16,000 grays per second. We can also use monochromatic X-rays to perform image guidance. So which are the characteristics of this part? We can produce a different size and a different number of microbeams which can be delivered in parallel mode or in converging mode to a target. Normally our target, or actually the target our users or our user program, is the central nervous system, either the brain or the spinal cord. We can produce microbeam arrays down to 20 micron wide or up to, of course, millimeter range. We can perform image guidance with the standard Frelon imaging tool available at the ISRAF to, let's say, identify with the high resolution, which is the target in the central nervous system, down to about 100 micron precision in vivo. The second part of the beamline, which is located outside the ring, at about 145 meters from the source, we have different monochromators allowing different energy range and different energy bandwidth. So to make it short, we can move from with continuity from 25 kiloelectron volts to up to about 200 kiloelectron volts. This, of course, allows a broad range of applications with coherent beam or double beam delivered to the sample, bichromatic. So the detectors, again, to make it short, we have different scales going down from 3.5 micron up to 350 micron pixel size. So we have a very large number of users and communities. And what is important for our users is the presence of an animal facility and the cell and molecular laboratories. We have also an histology lab, and for comparison purposes, we have also a conventional X-ray therapy unit. So we are involved in several projects, and the one that I would like to mention is the we are chair of a European coast project, which involves now 16 nations and is focused on applications of synchrotron radiation for molecular, for application of a therapeutical application and radiation surgery. So let's go rapidly to different possibilities that we can offer to the users. So the first one is having a bichromatic X-rays, like my friend Angelo Taibi has mentioned before, that can be useful for have high resolution mapping of a contrast agent which was previously inserted into a sample, for instance. So in this way we can provide a focus, two focus X-ray beams to the target and record simultaneously two lines corresponding to the two energies which are focused on the same detail inside the tissue. This allows a perfect subtraction of the images and avoiding any motion artifact because the two beams are simultaneous. We can apply this technique down to about 25 kiloton volts up to about 100 kiloton volts, covering most of the K ages, biologically interested K ages for contrast agents. One example of application, quite interesting and quite let's say published at a very high level, are the in vivo analysis of the effects of pollution into the lungs, or the origin and the effects of drugs to asthmatic animal models. So you can see these are computed tomographies of rabbits taken at different positions, vertical position at different height, closer to the brain or lower one, and during or a asthma crisis like below, or during a normal situation. So you can map and get a quantitative distribution of the ventilation inside the rabbits. This is just one of the possible applications you can apply in brain angiography, coronary angiography, and any kind of application where you have a contrast agent with a KH. Then another interesting characteristic of synchrotron radiation is the coherency. Recently, I had a school and I presented these slides, and they were quite happy to understand in a simple words what the coherence of light coherence means. So on the left side, you see the light coming through this window, which creates a very sharp shadow on the wall, on the floor. This light and this system, rather than light, is highly coherent because the shadow is quite well defined. On the right side, you see a system with lower coherency because the border of this shadow are much more phasing and less defined. Okay, this is translating in visible light what high coherent setup and low coherency means. And this is the simultaneous presence of this low coherency and high coherency. So if you have a high coherent beam, like in the case of synchrotron, you can apply imaging techniques that are not available, presently available using conventional sources, and you exploit the refraction of the X-rays inside the tissues. So what is refraction in simple words? Well, it's simple like a glass of water. You can, if you insert a pencil in a glass of water, you apparently see a change of direction of your pencil, which is actually determined by the change of direction of the light. And this is exactly what happened in the using X-rays. When the X-rays penetrate inside the sample and they come to the sample, they just slightly change direction. And if you are able to visualize the change of direction, you can get images of very high contrast. Unfortunately, I cannot go much further in details of this technique because it will take at least 20 minutes to explain that. But there is a clear equivalence of visualizing the refraction of the X-rays with the visualization of the refraction of the visible light. The only unfortunate case is that in the X-rays regime, you get microradians, so very tiny change of direction, so it's quite difficult to record with the normal X-ray sources. So with the coherent beam that can produce this kind of a phase contrast, as it's called, or refraction contrast, you can dramatically improve the images of very tissue-sensitive samples, like a breast, for instance. You get on the left the image acquired at the hospital of a breast containing a tumor, and on the right side you get the image of the same sample acquired using this phase contrast technique. There is no need to explain and to highlight the large amount of details that are lost in the conventional image, and these are overlapped with histology. The histology is the cut of the real sample, which tells you the truth. So as you can realize, the histology was very similar to the X-ray image. With this technique, you can try to reduce to the minimum the dose to the patient. Actually, we only apply till now to ex vivo but full breasts in computed tomography, which is not conventionally applied for screening at the hospital, because there is the risk of creating secondary tumors just is too high with the normal doses. And here you get the result of after application of this phase contrast as some in-house developed image reconstruction techniques. On the left side, you see a 3D rendering of a full breast using conventional source. And the right side, you see the same breast using this phase contrast. In addition to the dramatic increase of contrast, you get the difference at the bottom, where on the left you get about 50 milligray to acquire this image, and on the right side 2 milligray for an image of even higher spatial resolution, because this is 100 micron cube voxel, and on the left you have 300 micron cube voxel. This phase contrast technique can be applied to different kind of organs and tissues with a dramatic increase of contrast both on the bone and on the soft tissue. Here you get the comparison between conventional imaging, not on this image, but the phase contrast imaging of a full human knee post-mortem from a cadaver, and below the 3D 3 Tesla MRI. We go more in details. So on the first line, you get a comparison between the bone visualization on the one image and on the soft tissue visualization of cartilage between of the patella, compared with the conventional image. Again, you can get the dramatic increase of contrast and the precision. You can see inside the cartilage. And also you get very high information, very detailed information about the bone underneath, so the subchondral bone. If this is compared with 3 different sequences, MRI sequences, you can see that the cartilage can be very well also represented in some sequences, but not the bone. So with a single image, you can get very high diagnostic imaging, and let's say significant images of both the soft and the IZ tissue. We get more details in the next ones. But this is just to give you, this is a very recent result that just been published. Another application of phase contrast is for the visualization of the vessels and the capillaries. This is a rat liver to which was applied for research aiming at understanding stenosis of the portal vein, which is the main vein affecting the liver. And on the right side, you get the reconstruction of the vessel tree in an ischemic rat model and in a control model. So these veins and capillaries correspond to these small holes looking on the left computer tomography image. This is computer tomography. It's not a visual, it's not a picture. So here you can go down to a few micron and analyze which is the development of the vessels and the capillary tree, and even count how many branches have been created. This is what we are doing right now. I compare that with a normal sample. Okay, this is what just a few examples of the possible research using imaging tools of the ISRAF, and I will be delighted to answer to your questions.
Okay, so thank you, Alberto. A question for you.
Alberto, it's a curiosity. So do you have patients on your machine and you have human stay there and,
Yes, yes. I have two answers. So thank you for the question. So we have two therapy programs, one using the microbeams and one using monochromatic X-rays in combination with a chemotherapy. So regarding the microbeam radiation therapy, we reach the veterinarian clinical trials, which is a fundamental step where we receive animals from veterinarian clinics that are destined to die because there are no cure for brain tumors in cats and in dogs. So the owners bring to us, ask the veterinarian to enter in clinical trials where we do a sequence exactly as they were humans, so with the same kind of security and the same sequence of protocols. So we do a dose escalation. So we started with the first cat, we will get a second cat next week, and so on. So we recruit a certain number of patients to get the statistical significance. This will be an intermediate milestone before moving to human beings. Then we have the second clinical program using monochromatic X-rays, and there we are reach patient number 6 in phase 1, phase 2 clinical trials. I hope you know what means phase 1, phase 2, otherwise I will explain later. And there we are progressing up to reach the first phase, including 20 patients. Any new therapy needs some internationally approved protocols which have 4 phases, and we are, let's say, at the beginning of the phase 1, phase 2 that we were combined together to treat brain tumors, brain metastases right now.
Thank you. Any more questions? No? Okay. So we thank you again, Alberto. And,
thank you very much.
We move on.
Nice continuation.
So now, all right. So next speaker is me, actually on behalf of Chris Frost from ISIS. We have a new beamline coming up at ISIS that is rather special, which is using fast neutrons. And the main application, the driving application, is for irradiation of electronic chips. So in these few minutes available, I would like just to give you a set of slides that were prepared by Chris, and this is the problem we are facing, namely computer failures, but in general failures of the electronics, which is more and more widespread. So you get voting machines that can fail, and this was an example in Belgium. Systems, big systems that report, well, actually they are not reported, but they are failures in the electronics, and the cause is often the radiation induced from atmospheric neutrons. So these are not reported, of course, because it's not good publicity, but it's happening all the time. We want to minimize it, the effect, and there are there's a big effort from the electronic industry to make this effect as rare as possible. The cause for that is radiation, cosmic radiation, and once you are at a flight altitude or ground altitude, the main component is neutrons. So what we do in the lab is to reproduce the effect of these neutrons, but at a much faster pace. So what you see here is that on a coin size surface, this is a 10 pence example, you see we get in the order of 300 neutrons per minute if we are at these altitudes. And this is the type of fluxes that occur in the environment, and these are neutrons of energy above 10 MeV. In the lab, we can do accelerated testing with fluxes that are about 10 to the 6 to 10 to the 8 times higher. This effect at the microscopic level are due to interaction of the high energy neutron with the oxide in the semiconductor circuitry, and that is causing extra charge, which is then ultimately changes the logic level of memory bit, for instance. So what you get is a bit flip, and this is the most common effect. There are also harder effects that lead to damage, which can be recoverable. Namely, you reset the system, and that's called the latch up. Or if it's not recoverable, then it's a burnout event. These are usually due to higher energy neutrons. The recoverable errors are more often due to neutrons of lower energy. And with the scale of the electronics going down, now it is becoming more interesting also to look at effects due to neutrons from energies of 1 MeV and above. So I will accelerate a bit, but this is probably the worst accident due to neutron-induced failure in electronics on an airplane. I say probably because it's not certain, but all other effects and possible causes have been ruled out, and you can see what happened to the people that had not their seat belts fastened. Nobody got killed, but some people got injured. This was a Qantas flight, and it occurred, well, Basically, what the airplane did was to go down in altitude suddenly, and that, of course, meant that people and objects were moving and hitting in fact, the ceiling of the airplane, and you can see the effect here. So luckily, nobody got killed, and yes, it's comparable to the effect of a roller coaster drop. One of the, and of course this was investigated quite in detail, and it was mentioned in the report that one of the reasons the electronics on that airplane had not been fully tested was the lack of appropriate test facilities. And this is true, namely there are very few facilities around the world where one can do that. So out of this need, I will skip a few, comes the cheap IR beamline at ISIS. Then the idea is that by having a penetration in the beryllium reflector looking at the target, one can extract a fast neutron beam of the required energy spectrum, and this is then corrected by the use of a secondary scatterer, delivering in the end a beam which can be tailored in terms of shape and intensity. A pencil beam means a beam of a small cross-section. Flood beam or flood room is when, in fact, it's like a spray over of neutrons over a system that can have a size of a cubic meter and larger. So we go from, in principle, from irradiating individual chips all the way up to cubic meter size samples. Let's see. Okay, I have to be brief because time is passing, but I will perhaps give you an overview of the beamline as it is. You can see here the path neutrons have to move, in fact, is not straight, and this is due to specific constraints at the of the target geometry. But that is also a feature that can be used to the advantage. So you can see that here at this angle, it means that neutrons will be scattered in this area, and they enter the interaction, the blockhouse from collimation system and shutter as usual. You can see here, even if it's small, there will be, once the neutrons are out of the shutter and collimation, we have two tables, one for small samples and one for large samples. This can take up to 500 kilograms in weight, and so this is rather large items. The access door is reasonably wide, and we need a specially thick collimator, beam dump. The neutron spectrum looks like this. You can see this on a log scale. It's a fairly universal curve. These are spectra reported from other facilities worldwide: Triumph in Canada, Anita in Sweden, Lance in Los Alamos, United States. So, and the dotted line is the industry standard for what the neutron spectrum should look like. Doesn't mean it is the true spectrum or a measured one. It just means that this is the standard. And so if you want to have a facility that complies to this standard, it should match this spectrum as closely as possible. Until maybe in 10 years or 20 years from now, the industry will agree on a new standard, and then we have to adjust. But this would be, in any case, small adjustments, because, as you see, this is a rather typical curve. More or less, all facilities provide the same spectrum, not exactly the same. There are differences, of course. So Anita in Sweden, you see, drops out at about just over 100 MeV, because the proton beam has a lower energy there. CHIP-IR should go up to the proton energy, which is 800 MeV. I will skip then more details, but I show you examples of cross sections. This is simulated, of course, of the beam, and you can see that these numbers are centimeters. So in this case, we have about 20 by 20 centimeter area where we have a fairly uniform beam. So irradiation of a 20 by 20 area with a beam of fast neutrons. Well, you can see here the more accurate numbers. And by using the collimation and adjustment, we can make this smaller, and this is an example of how it can be changed. Other changes that can be done is a set of filters that can be used to tailor the neutron energy spectrum to some extent. You can see here different phases of the construction. At the moment, this is the inside, where you can see the moving table and the other smaller table. At the moment, the beam line is under construction, and there are first tests in progress, and we should have this got stuck for some reason. Or maybe it is another presentation. Okay, no, never mind. Yeah, I think we had this. There was a newer version of this presentation with another slide at the end, because a comment that I wanted to make at the end was that since the focus here should have been more on the biological systems, I would like to mention the possibility that needs to be explored and later tested of using fast neutrons, so a fast neutron beam like the one we have here on CHIP-IR, for irradiation of biological samples. An example could be trying to replicate the effect of cosmic radiation on live organism on a space station. So the International Space Station one day may have vegetables, or we should see it. I mean, in general, whatever live system is in space, we send in space, will be subject to radiation. This will not have exactly the same features as here, but it is interesting to expose it to different types of radiation effects. And there are not many places in the world where one can test specifically the effect of fast neutrons at these intensity levels. Because reactors will give you plenty of neutrons, but they are typically of lower energy. So this spectrum is, in fact, quite unique of spallation sources. So I think this is a possibility that should be explored, and maybe there are other examples of problems in bioscience that I'm not aware of, since I'm not from that field, where this type of beam fast neutron beams could actually be used for new experiments. And that's all I had to say. Thank you. Okay. So we are about one presentation late, or 1.5 actually. But we have quite a generous lunch break, so we can use that. Any questions? Yes.
Is there any interest from the Italian electronic industries, ST microelectronics?
Okay, that's. Thank you for the question, because in fact, ST Microelectronics carried out tests, in fact, an assessment of the use of another beamline at the time when it was decided to build ChipIR. So this was a few years ago. So they are definitely interested in this type of experiments, of this type of testing. So ST Microelectronics, which is companies evolve, so I don't know the latest, but it was half French and half Italian, at least until some time ago. And so there is a group that is specialized in this type of testing, and so they have been at ISIS before, and I am confident they will want to be back when ChipIR starts operation. ChipIR will not have the full conditions for irradiation until next year, because it needs, now there is the need to change the target assembly. I mean, the hole in the beryllium reflector that I showed at the beginning will be, in fact, achieved by replacing part of the target assembly with new components. And that is happening at the next large shutdown. So we should have neutrons in ChipIR starting from March next year, hopefully. So if there are no other questions, I would move to the next presentation, which is the final talk for this morning, given by Sandro Silvestri.
Ma forse?
Here it is. Sorry.
Eccolo qua. No, c'è qua, no, va benissimo, uso questi. Sì, uso questi.
Okay, so Professor Sandro Silvestri, he will tell us about extreme photonics.
Okay, so I want to give you the introduction on which are the major highlights in laser research. We have two extreme goals right now. One is watching and controlling the electron motion in real time, and we call this attosecond science. So we should enter in the time regime, which is of the order of 100 attoseconds, below the femtosecond time regime. Then the other extreme is laser particle acceleration by using ultra-high intensity light. So these are the two major research lines going on in the framework of laser research right now in Europe and also in the rest of the world. And here there is the timeline of ultra-fast optics, or the timeline which is give you an idea of the development of ultra-short pulse duration over the year. We start around the 70s with 1 picosecond, more or less, using dye laser, so-called dirty laser, because dye lasers are difficult to handle. Then we went to the so-called solid-state lasers, so much better handled, it's more reliable, and the pulse duration went down up to maybe a few femtoseconds. And then using very highly nonlinear order techniques, which is called high-order harmonic generation, it was possible recently to go down the 1 femtosecond line and to go down to something which can be right now about 50 attoseconds. At the same time, we have seen an increase in the peak intensity of the laser, thanks to different mode of operation, started with mode locking, then this is called the chirp pulse amplification, which is a new technique which was developed in the around 84, 90, and then we see a continuing increase, and hopefully we will be able to reach this region where the intensity is about 10 to 25, where we can have relativistic motion of the electrons and particles in general. So these are the two timelines of the pulse duration and the intensity. Okay, the scenario of the research, European research, of the European laser research is the following. We have the national labs infrastructure, which are the basis, we call the basis. Then we have a decentralized pan-European infrastructure, which is a sort of network of infrastructure. This is a flexible instrument for new challenges, highly interdisciplinary. And then we have the pan-European infrastructure, which are in the ESFRI roadmap, European Science Forum for Research Infrastructure, and these have a well-defined mission and worldwide interest. So this is the way the laser research is organized right now in Europe. Regarding this part, so the fact that we have a sort of, let's say, network of laser infrastructure is more or less linked to the Laser Lab Europe. So Laser Lab Europe is an integrated initiative of European Laser Laboratory. Here are all the laboratories involved, and they act in a sort of coherent way, coherent action. And we have about 30 laser infrastructure in 16 countries, then subcontractor, associate, and so on. And in Italy, we have two infrastructure which belongs to this network. One is Cusbo in Milano, and one is Lens in Florence. Okay. The infrastructure in Milano was established in 2001 and grouped together different actors, the Department of Physics in Politecnico, and the Institute of Photonics and Nanotechnology of the National Research Council. The kind of activity are related to ultra-fast science, so ultra-short pulses, ultra-fast processing quantum confined system, coherent dynamics, nonlinear optics and high-intensity laser matter interaction, and attosecond science. Then the biomedical optics is related to non-invasive optical characterization of biological tissue, fluorescence lifetime imaging, spectroscopy of diffuse media, and diagnostic and functional optical imaging. So this is the panorama of the research going on in this research infrastructure, which belongs to the European Laser Lab Europe. Then, as I have shown you before, there is the roadmap of European Strategy Forum on Research Infrastructure, and two big laser infrastructure were selected. One was HYPER, European High Power Laser Energy Research Facility, which is mainly for civilian laser fusion and research. And another one is Extreme Light Infrastructure, reaching the highest laser intensity and related application. Okay, I will talk about this one, okay, because this is going to be built in the next few years. This one has to wait, of course, some more development in the field of fusion, because we know that it's very difficult at the moment. So regarding the LI, so the Extreme Light Infrastructure, this will be the first international research infrastructure which can, thanks to the extreme, so the high intensity, pursue unique science and research application for users. LI will be implemented, the distributed research infrastructure, mainly on 3 specialized complementary facility. One is located in Czech Republic, one in Hungary, one in Romania. LI is the first S3 project which will be fully implemented in the newer member states. And LI also is pioneering a novel funding model, combining the use of structural funds for the implementation and contribution to an ERIC to the operation. So this means that the construction of these 3 facilities, which will go on in those 3 countries, mainly rely on structural funds. These funds, of course, are devoted by European Union to developing the region of these 3 countries. So instead of building a highway or a beach or something like that, they they have decided to build a scientific infrastructure. So I think this is a very interesting decision on how to use the structural funds. And in those three facilities, there will be attosecond laser science, and this will occur in the facility in Hungary. Then another facility is high-energy beam facility. So this is the generation of intense X-ray radiation and short pulse duration, a laser plasma acceleration of electron and ion for studying biomedicine and material science. This will be in Czech Republic. And in Romania, as you heard before also from the talk, you see that a nuclear physical facility, ultra-intensity laser source, combination of 210 petawatt laser source, and also high brightness gamma ray source, which is the for nuclear physics studies. Okay, roadmap, governance, and financial situation. We had the preparatory phase. Then now we are in this phase where there is the implementation. The cost for this implementation is 150 mega euro, and this money comes from the structural funds, essentially from the structural fund. And then after the construction, there will be a joint operation scheme, and of course with some operational costs, which in that case are not covered by structural funds, but they have to be somewhere found in the context of, let's say, supporting activity of infrastructure. Okay, there is a sort of, let's say, organism which is now dealing with the construction, which is called LDC, Early Delivery Consortium. And for the moment, Germany, Italy, Czech Republic, Hungary, Romania are taking part. Then there is UK coming and probably also Greece coming. And in the Italian side, we have the INFM, as you heard before, and also the National Research Council with 2 institutions, and the synchrotron and Trieste. So these are the institutions collaborating to this kind of initiative. INFM is leading the European consortium, which is called the Eurogammas, and this is for the construction of a gamma ray source by Compton scattering. This performance will be 100 times better than the state of the art, 19 MeV, a certain number of photons, and a very short and a very narrow bandwidth. And this can provide a unique feature for experiment in nuclear physics. And the project responsible is Luigi Palumbo, and the scientific responsible is Luca Serafini. Okay, this is a contribution of INFM to the project. This is a very large project, 60 million euro, and it has been already approved and is under construction. Then the National Research Council is participating with 2 institutes, the Institute of Photonic and Nanotechnology in Milano, and then the the National Institute of Optics in Florence and Pisa. The Institute in Milano is mainly collaborating in the generation of attosecond pulses, XQV molecular tomography, optical instrumentation, XUV. And the National Institute of Optics is mainly collaborating on particle acceleration by laser plasma interaction, generation of intense X-rays, and also development of a diagnostic therapeutic technique based on laser particle acceleration and X-rays. Okay, these are the 2 main contributions of the National Research Council to the project of ELI. In particular, the INFM, so the Institute in Milano, in Hungary, because Hungary is where there will be the attosecond facility, is right now implementing 4 attosecond beam line for user and R&D. Those should operate at 100 kHz for pump probe experiment in XUV and in IR and XUV with 100 attosecond resolution. The TDR is completed, and we are entering right now in the contractual phase. And this is just the design just to give you an idea of what is a beamline, attosecond beamline, and how it works. The main topics at LI Alps, so at LI in Hungary, are valence electron science, core electron science, attosecond imaging, probably in 4 dimensions, relativistic interaction, compact high-brilliant sources for biological, medical, and trans application, and manipulation of matter by intense TRS field. So these are the kind of activity that is going to be covered in this facility in Hungary, where the attoscience will be developed. Maybe I just give you an example of what can be done with the nanosecond pulse. You have a PAM pulse in extreme ultraviolet. Then this is glycine, for example. Then you have an attosecond pulse coming in, attosecond ionization. This creates a hole which moves around the molecule in a very fast fashion, and then you come up with a second probe, which can be in IR or another XUV, and then according to the delay between the two, you can have a breaking of one bond or another bond, depending upon the position of this hole which has been created by the initial pulse. So using these very short pulses, attosecond pulses, it's possible to follow the dynamic of the electrons, the electron dynamic in a molecule, which is usually very difficult to see. And so what we are usually going to see are maybe nuclei movement, vibrations. We are maybe ready to see the energy relaxation, but we are not able still, if we don't use very short pulses, to see electron rearrangement of a molecule in real time when you create, for example, a hole here by the electron ionization. So this is just give you an idea of the potential of the attosecond pulses in following the electron dynamics inside the molecule. It may be able to control the bond breaking of the molecule according to the position of this hole during the migration along the molecule. This is just an example. Okay, maybe I thank you for the attention.
Thank you very much for this very fascinating enterprise.
Yes.
Okay. Last questions before lunch. Yes, Beatrice.
I do apologize for the somewhat naive question, but could you mention biological and medical applications? Because you said that this consortium does have.
Yes. One of the problems maybe is the possibility to understand the DNA repair mechanism, the DNA damaging mechanism, and how they can be. Yes, this is one of the main research field is in the DNA repair mechanism and damaging mechanism.
Sorry, this is probably quite a simple question, but
yes.
I know nothing about this. You said about looking at the electron or dynamics rates yes. based on doing this process. But this is presumably an average technique, so when you throw in this attosecond pulse of a given frequency or wavelength on the CC bond and the glycine, this will break all the glycines in the system, right? If you had a protein. So then you would get an average picture?
No, you don't get an average picture. Depending upon the delay, because the delay is related to the position of the hole of the electron. The delay is related to so each time you do this, you repeat the experiment. And depending upon the delay, you have a different bond breaking. So you don't have an average picture. So as a function of a delay, you have a different situation, if I understood your question. Okay, so the averaging is done each time on a fresh sample, in such a way that you have each time a new molecule, and then for a certain delay, you make the measurement, and you repeat this measurement many times, and you have an averaging signal-to-noise ratio. This is only the point. And then you change the delay, and you repeat, and then you change the delay.
Thank you. So, if there are no more questions, I thank the speaker again.
Okay.
And we should get back here at 2:30. So we have 1 hour break for lunch. And I would ask all speakers, there's a form that you should fill in, just sign in order to, that's clearance for broadcasting your presentation, which we have done already, but and also to keep the record of it on the database. So the forms are just on the table outside. Thank you. Oh, and those who have their talk in after lunch, if they can upload the presentations now. Thank you. So, thanks for coming back, and we should now move on with the next session, which is more of Module C. And we have 5 speakers. First one is Victoria Garcia Sakai from ICIS, and she will tell us ICIS neutrons for biomedical challenges.
Thank you, and thank you for having me. So I'm going to concentrate on giving you some examples of biophysics related towards the medical type of application, applications of why neutrons can help to answer some questions. But I would say from now that the instrument suites we have at ICIS are similar in some sense to the ones that you can find at the ILL. So even though I have no examples from the ILL, a lot of things can be done in both facilities in a similar way. So I'm actually not a biologist, but I do come from a polymer science background in a sense. So for me, all these biological molecules in a sense are still macromolecules, just they have a function. So the most important thing, I think, for a lot of these macromolecular systems is the fact that they have a hierarchy of length scales. So, and all things are important for the final function in the biological sense. So from the really small length scales like atomic displacements to how they are arranged to all the way to the tertiary structure and how the tertiary structure then interacts with other macromolecular bits. So like here you have a protein interacting with the lipid membrane, and this hierarchy of length scales needs to be accessed in its full. Of course, the mixture of different macromolecular entities for biological systems gives rise to this complexity, and as has been mentioned already, neutrons are quite key in this. Since you can deuterate and protonate bits of the samples to be able to decipher this complexity and look at individual pieces of these puzzles. The second thing which is important, so not only the structure, is that all these entities are non-static. So proteins in solution are constantly moving in water, and so flexibility is extremely important for function. And so we also need to look at what happens in this hierarchy of timescales, from, say, femtoseconds, as we saw before with the electrons, all the way to microseconds. So at ICES in particular, to look at timescales, we have a series of instruments that cover the entire range. So we go from the really fast motions that we can look at with things like Vesuvio or Tosca, which looks at vibrational modes, through the more picosecond to nanosecond scale dynamics with different spectrometers. This is just how they work through direct geometry or inverted geometry, all the way to a new project, which is a SpinEcho-based system that essentially will give us timescales, hopefully, of 10 to 100 nanoseconds. And this is already possible in places like the ILL with the SpinEcho instruments. And in parallel to that, of course, as I said, we have the multiple length scales, and we can also achieve this at the moment at ICES. We have a number of instruments. These are the newest ones, I guess. We have the small angle scattering instruments, such as this. Zoom is a new project which will extend the length scale to larger objects. Then we have Nimrod, which covers essentially the really, really small scales and overlaps with the small angle scattering instruments. And then, so this would be sort of the structural analysis equivalent to SACS. And then we have the reflectometers, which look at depth profiling and surface behavior. And these are the three reflectometers in the second target station. So these are the newest of our instruments. Of course, for biological systems, it's not just neutrons that we need. We have a very big biological lab, I would say, where we can do a number of things. So we provide the support like bacterial growth, protein purification, and then we have a lot of characterization kits like DLS and that kind of stuff. And then, as has been mentioned before, we have a deuteration facility which we inherited from Bob Thomas's group in Oxford. This is primarily for deuterating small molecules. So, for example, oleic acid. We can also do things like lipids. If you want bigger deuteration entities like proteins, then the ILL has a dedicated deuteration lab, and we work very closely with them to do this. So what I'm going to do now is just go through some examples of things that have been done at ICES. I've tried to pick things that involve Italian users of some sort, just to put it more to home. So this is a very, very recent example, and I kind of like this. We've just run this about 2 weeks ago on the iris spectrometer, and this deals with looking at proteins or bacteria that live in very high pressures in the bottom of the sea, in the Mariana Trench. And they wanted to understand how these bacteria have actually adapted to live in such environments. So with the help actually of the ILL, we've borrowed this high pressure cell from Daniela Russo that she developed, which is very nice because it has an annual geometry, which is what we need for our spectrometer to avoid multiple scattering effects. And Fabrizia Foglia from UCL has used this to look at these bacteria at 5 kilobar pressure. And this is just data that we haven't really analyzed because it just came out. But essentially, she has bacteria, wild-type bacteria, and then she has bacteria that she adapted in the lab to 7 kilobar. And basically, what we find by doing the experiments is that the flexibility of the protein that has been adapted is no longer affected by this extra pressure that we put on, unlike the wild-type bacteria. So this will hopefully give us some indication of how the protein flexibility changes with pressure. The next example is trying to use, both X-rays and neutrons to look at both structure and flexibility of a small molecule, in this case ethanol, which is used as an anesthetic, to try and understand how it interacts with the cell membrane. So first of all, how to understand what the anesthetic mechanism is, but also to give us a clue of why really we get drunk when we drink. lots of alcohol. In fact, ethanol does it modulates cell membrane proteins. If you put too much of it, actually, it breaks down the membrane structure. But more importantly, is can we understand how it works as an anesthetic? So this is an example of complementarity. This is X-ray patterns that we look at with just an X-ray machine in the lab, and we can look at in-plane and out-of-plane. It shows essentially that ethanol molecules do go into the cell membrane, which is something we didn't expect because the interior is, of course, hydrophobic, but some of it goes in. But also, by looking at the dynamics of the membrane with the ethanol, we do find via neutrons that the dynamics changes a little bit. So ethanol enhances this modular movement, and also, in fact, it gives rise to the so-called ripple phase, which is harder to see, and we're still trying to understand it. The other thing we've done about a couple of months ago is with LET, which is one of our newest spectrometers, like the type of iron 5 at the ILL, and the fact that they have position-sensitive detectors, we've been able to, in essentially one go, just put stacks of bilayers, and by looking at the length scale versus time, look at, in fact, in-plane water diffusion and out-of-plane water diffusion. And we will do this, we've done this with water initially, but we will do it with ethanol by deuterating and hydrogenating different things. And this is only has been possible due to these position-sensitive detectors. This is a bit older work, moving to drug delivery. So this is work by Antonio De Rio's team in Parma. This is trying to create drug delivery vectors which are based on lipid complexes, and the drug would then be inside here. By looking at the dynamics of the lipids and how that is affected by different, in this case, for example, they've added a small additive with chitosan or this IPM. They want to look at the stability of this vector over time, and so they've basically looked at how does the dynamics of the lipid change with and without additive. You can also look at these drug delivery vehicles from a different point of view, and this is by looking at the water. So how efficient is the drug to come out of this, to be delivered essentially, to come out of this particle. In this case, these are very commonly used 9' hydrogel, so they make these micron-sized spheres. The drug sits in the middle, and you can look at how the water diffusion in and out as a function of temperature, because these kind of swell and collapse as a function of temperature, and they can look at the water diffusion, and that tells us something about how fast the drug will be thrown out, I guess, or delivered. And this is work by Gaio Paradossi's team in Rome. This is a third example on drug delivery. This is moving from oral drug delivery vehicles and trying to find an alternative. So in this case, they want to use the transdermal delivery path. So this is like with a cream or with a gel or even with this type of patch. And they want to understand how the drug would go through the skin barrier. So they've used neutron reflectivity to look at the interaction of the nanogel, this is again a NIPAM gel, through a mimicking membrane which they made of ceramide. And so you can look at where the nanogel sits in the membrane and how it goes through. And you can do this with neutron reflectivity. This is a very recent example, not drug delivery now, but this is in a little bit to put it in parallel to the X-ray crystallography, for example, information that we were talking about before, or that has been talked about. Steve Perkins' group in UCL has been trying to see if from the X-ray structure of this antibody, if they can learn actually how it behaves in solution. So this antibody is used in a drug for multiple sclerosis, but it seems to affect the immune system. And so they wanted to see how it is that it works in doing that. And so they've measured the structure using SANS, so small angle X-ray neutron scattering, and tried to figure out these different bits by deuterating the different bits, how this works. And what they found out was that these arms actually seem to get in the way of this FC center, and this doesn't allow some antigens that are in the immune system to interact with it. And so it seems to work in controlling white blood cell migration across the blood. And this is a joint project between the X-ray structure and then the solution structure with neutrons. The last example I have is on this work, which is also extremely recent from the University of Manchester, and they're trying to understand how to make more reliable pregnancy tests. So this is a regular home pregnancy test, and the way this works is that when you're pregnant, this hormone HCG is in high levels in your urine, and so it goes onto the test strip, and there's an antibody, this one, anti-A, which has a blue label, and that is supposed to capture the HCG and then diffuse down to the test area where it joins up with another antibody B, and then if this basically gets made up, then it'll tell you that you are pregnant. What's happening though is you get a lot of false positives because this little molecule here joins up like that, and it actually diffuses through, but actually either joins with other proteins in the urine and gets to here still, or just the blue label gets to here and then it doesn't, you're not actually pregnant, but because you need these two things to join up. So they've used basically neutron reflectivity to try and understand how these molecules sit on the surface of this test strip and see if they can figure out how to get rid of, or how to make this whole thing a bit more specific. And what they saw is that in fact they don't sit up, so they expected this arrangement to happen, but in fact they just sit flat on the surface of the test strip, and it can actually create blockages so that they don't diffuse through, or as I said before, this little molecule just goes to the test area, shows you that you're pregnant, but in fact because it hasn't joined up with anti-B, then you're actually not. And I think I'm going to leave it at that with the examples. But anyway, I hope it's given you a sense of what kind of things you can look at with neutrons. For more information, either you can ask me or just go to our website and we'll direct you to the right person. And then I'm just going to leave you with something which I thought is relevant for this audience, which is a meeting that is happening in Abingdon, so about 8 miles from where ISIS is, in September, which is basically a workshop on neutron characterization in fundamental and applied biochemistry that you might find useful. So thank you very much.
Thank you.
Questions?
Vicky, sobre la... sorry, I started in Spanish. About the first example you proposed, of bacterial living under the sea.
Yeah.
I can remember there's some work done on Iron 5 from Paolo Caligari. You don't know about it? So maybe it should be something to check. It's not the same bacteria.
Okay.
But it's the same kind of, microorganism living at high pressure.
Okay.
I think was done 5-6 years ago. Okay.
This one I don't know.
I think that one was high temperature. There were thermophiles, extreme. I think they were temperature. Anyway, yeah. Okay, anyway. But I didn't quite understand so you had bacteria which were pressure adapted in the lab, which didn't show any change.
No, when you apply the pressure again.
But the other one did. So you think the one that is adapted to an environment wouldn't be sensitive to, or is the one that's adapted to the environment no good at low pressure? But then I didn't quite understand this.
So, as I said, this is like 2 weeks ago. So the one that's adapted to pressure in the lab doesn't seem to show any
effect to pressure.
Effect to pressure. Exactly. But the wild type, which hasn't been adapted to pressure, cannot withstand the pressure.
But what does adapted to pressure in the lab then mean? Does that mean
they basically pressurize it?
And it can live?
In the lab, and it can live, yes.
Right. Okay.
I'm not sure how you pressurize bacteria, but that's for later. Okay, so no more questions, and we thank the speaker again. And next is Gabriele Biella, who will tell us on synchrotron and brain, a magnifying glass on chronic pain.
Thanks for inviting me. Now what I will show here is some results that we obtained at SRF and Grenoble with animal models of chronic pain. And my lab is working on chronic pain and sensory disorders, basically with electrophysiological techniques, recording massively from neurons in the brain, both in animals and in humans, at the neurosurgery department in Pavia. And I will propose also the next project we are just starting in September at SRF. Well, let me start here. Okay, these two are, let me see here, because I'm an almost blinded man. Okay, thanks. And these were the two projects on chronic pain we did in the last 2 years. The first was on a sensory motor cortex transaction to study the neurocircuitry of chronic pain, and the other was called more simply microbeams, like X-ray from pain relief. Basically, these are two equal projects based on two models, animal models of chronic pain. And chronic pain needs some, and our approach needs some technical and theoretical preliminary. So I will ask your patients to follow me in few steps into this field. And you can see here, let me see, okay. You can see here a rat brain, and these are two experimental situations, one in acute recording from the brain, from these two areas, the somatosensory cortex and the thalamus. These are two major stations of the sensory pathways, and they are deeply involved in chronic and in acute pain. And these are the signals taken from the brain. Obviously, here are reported only few traces. The traces are much more, and we can gather either the full neuronal signals that are called spikes, or in larger thresholds of recording, we are recording both spikes and these slow events that are called the local field potentials. Spikes are just a popping neuron like that, and these are just the neurons talking with us, and these slow waves are instead the activities in the synaptic compartments where neurons gather and exchange messages. So we have a double phase recording at the synaptic side and on the cellular side. This is an acute approach, and this is a chronic approach. This rat has an implant in the brain, just getting the same two regions, with a number of electrodes getting in the thalamus and a number of electrodes getting in the cortex, and it behaves very quietly without any discomfort, and obviously all the operations are carried out under the international guidelines. So there are different models of chronic pain. Basically, these are two neuropathic models, and there are also inflammatory models, and so on and so on. It's useless to put here the complete list. The neuropathic pain is one of the most challenging situations in the clinics, and we have patients who also try to suicide them because the pain is intolerable. And it is one of the most challenging, most expensive pathologies we have in Europe and in the Western world, recognized as a crucial situation in the clinical treatments. So I showed you before the cerebral cortex and the thalamus, and imagine to have here that a kind of a representation of the somatosensory cortex, that is the cortical area receiving the sensory inputs. And as you can see, I put here just as a kind of metaphor, different colors here, because the somatosensory cortex is a very changing structure, functional structure, and it computes the many signals coming there. So we have a very changing and fluctuating landscape. When we have a situation of chronic pain, we have a strong, as you can see here, just as example, or intentional example, a stronger freezing of the situation. The neurons communicate among them in a very stable way, and it is a kind of frozen situation. How it is computed, this situation? It is computed by techniques taking source from information theory, the classical Shannon or Kolmogorov information theories, and from graph theoretical and from a graph theoretical approach. So we have here the two brain areas. These are the traces that I showed you before. This is one of the many probes we use. This is a 9 to 12 channel probe. And this is a kind of matrix saying when there is or not a spike into the trace. And we have a number of traces here that is a reduced number in comparison to the experimental situation. So we can gather all the data and build up a kind of circuit here in order to understand the property of this circuit. And as we know from graph theory, we can have either a kind of totally of a low degree connectivity, and there are only hubs here and there where each node of the connections is connected to few other nodes here. And it is the opposite situation where all the nodes, it is not like the true situation, where all the nodes compose a kind of lattice, all connected with all. In the midst stays a golden situation where hubs of connectivity are connected among long-range connectivities, but not completely covering the connectivity range of the networks. So this golden range and this golden image is the basic situation that we find in the brain. But what happens when we get a chronic pain model. When we get a chronic pain model, we can study, for instance, some measure. One is the thalamocortical redundancy, that is how much the same information is transmitted in the brain, and we have in normal rats this kind of result, and in the circuits of animals with chronic pain, inflammatory or neuropathic, with this kind of ranges in these box plots. This means that we have a kind of enormous increase of redundancy of signals into the chronic pain thalamocortical circuits in rat models. And here is again, there are other two measures with transitivity and with oh my God, clustering coefficient. Clustering coefficient means that how much the circuits tend to cluster blocks of neurons talking among them and not with other neurons. And as we can see, we have an increase of this clustering coefficient, and the complementary figure is like that, with the transitivity, that is, the connectivity among these neurons falls down. So this is the same thing that I just explained. This is the normal situation taken from a recording of us. This is in normal animals, and it is a graph representation of the thalamocortical circuit. This is in inflamed animals, and it is in two neuropathic models. These heavy arms show in some way the redundancy of the signals exchanged within the circuits. In some way, just because the majority of you is a physicist, I put also this image, and where we observe a redistribution from heavy-tailed distribution in normal rats to Poisson-like distribution of the synaptic connectivities in the brain. So how we organized the experiment in Grenoble. The two line experiments were the very same in some way. This is a deeply anesthetized rats with an X-ray detector here, and we have again the same cartoon as before. We have in normal rats this very vividly information exchanging area, and we have here a kind of freezing, as I just showed you, freezing of the dynamics of the cortex. But if we get cuts, 7 cuts by collimated X-rays in this region, taking off this kind of cuts like that, like those, they are obviously all equally spaced, but I wasn't able to equally space also in PPT the picture. So what was the intention of this experiment? As you can see here, this was what I in some way foresee for the result of the experiment. The frozen situation of before had to undergo a kind of change, allowing for a different neurodynamical destiny of this SS1 area in cutting slices by the X-ray beams. And this should mean that we should have enriched the information exchange in these areas. And these are the results. From a behavioral point of view, I don't stay here to explain deeply all this stuff, but this is the situation of some sensory experiment measuring the threshold, how much the animals were perceiving a stimulus, not painful stimulus. This is after the implantation of the chronic pain model, and we have a strong reduction thresholds. That means that the rats were much more responsive, and this is the result after the 7 being cut. This means that the cut, and here with another kind of experiment, this means that the cut were in some way given back some responsivity and some clear responsivity to the rats. Here I will try to show you the hoping that the film is going. Otherwise, I will show you. I will explain you how it is. The rat here is a normal rat, and it puts the paws just on the floor like that, as a normal situation. With the chronic pain treatment, the paw treated is retracted and deeply sensitive to stimuli. After the 7 beams, the rat was normally responsive, and with the paws again placed flat on the floor. So in light microscopy, we can see here the cuts that we obtained in the cortex, and in scanning electron microscopy, we have here the 7 cuts in the cortex that are barely observable in light microscopy, because these are 7 cuts with 100 microns or 50 microns in width. That is 4 to 2 cell diameters. So they are very, very low degree damage generating rays. These are in higher magnification, the cuts with kind of glial reactivity here. And this is also the report on the chemical composition of these cuts. In electrophysiology, with the electrodes that I showed here before, with the 7, these are the situations we get in different experimental conditions. I want to put your attention here and there, and you can see that the functional connection graphs give the same results in 7 being treated rats and in normal rats, as well as in functional integration. And this is the last project that I am just starting in September, microvessels in chronic pain, where microvessels are really 7 to 8 to 10 diameter vessels in the cortex, and we have a kind of strange displacement of activating areas in the brain, as in comparison to normal situation when the brain is activated here. But in chronic pain, we show the bold signals in fMR, that is the blood signals in chronic pain. And this is a fine image by David Kleinfeld of the vessel cohort here in respect to the sensory cortex in the brain. And the problem that we put is, and this is the last thing, is that the neuron is here. This is the glial cell that is the bridge between the microvessel and the glial cell. Is a kind of babysitters of neurons, giving them foods, oxygen, and so on and so on. In chronic pain, we have disorders in the architecture of this triad, and the problem is how much is disordered in chronic pain, this architecture. And if we discover this disorder, we can understand that chronic pain is also a neuronal glial vessel disorder. And this is just the cortex of the rat brain in anesthesia, with the dura mater and without. And this is just our question on vessels. and neurons. Thank you for your attention.
So as far as I understand, you were using the synchrotron X-rays to irradiate the brain. You're not using them to study it.
No, in this last I really
right, but in the first one you were using it to irradiate.
Right.
So you'll take, I mean, normally when people are using these X-rays to study biological materials, they worry about the damage. So, I mean, how long was this irradiation?
The irradiation is not long, it is just a snapshot, and the tomography, reconstruction of this architecture.
No, but when you're using it to irradiate, in the previous example, is that for a microsecond or a second?
Microsecond, I hope.
So what, I mean, what do you think you're doing there? Are you, I mean,
Because it is done not on living matter, but on pieces from the cortex, taken out from the cortex.
But you had a picture of a rat.
Well, the rat before is the rat in the previous experiment when I just cut the cortex.
But that's irradiation. You're irradiating. You've got a live rat.
On the next experiment,
yeah, no, but but in the first one, you've got a live rat, and you're irradiating a section of brain with a very high intensity X-ray beam. With a very high, I mean, it's a synchrotron, right? So it's an incredibly high intensity X-ray beam. So why did you think to do this in the first place? I mean, have you done this with a low intensity beam and found it produces nothing? I can't quite understand how you decided to do this experiment. Yeah, but what made you think that irradiating a brain with high intensity X-rays would have any effect on pain at all? Ah, right, you're not irradiating the brain, you're actually doing surgery.
I am a neurologist, you know.
But it's surgery. You're using, it's like a laser. A surgery, okay. So it's not irradiation, it's surgery.
No, they were sliced.
So it's not irradiation.
No, it's surgery. Okay. So
yes.
You can teach me how to do that.
Cyberknife. Okay. So I think we thank the speaker again and we move on. No, non trovo più il secondo microfono, ma si vede che l'avrò nascosto. Ah, ok. Grazie. Okay, it is now time for Francesco Da Capito to tell us about GILDA, the GILDA beamline at ESRF.
Okay. Can you hear me? Good morning, and I will talk to you about the activity of the Italian CRG beamline at ESRF. Presently, it's called GILDA, General Purpose Italian Beamline for X-ray Diffraction and Absorption. It's a project jointly financed by CNR and IFN. It's operative since 1984. It's 20 years that we are active at ESRF on a bending magnet source of the third ring. Normally, we made around 25 experiments per year with an outcome of about 30 publications per year. And we are mainly concentrated in these latest years in X-ray absorption experiments, both for what concerns spectroscopy or imaging. And now we recently passed a review 5 years review we always have from the SRF, so we are ready to sign a new 5 years contract, operation contract with ESRF, but during this contract we will take out the reconstruction of the instrument. We have been funded for this, and the new beamline will be called LISA, Linea Italiana per la Spettroscopia d'Assorbimento ITS. That will be a completely new project, but I'm not going to describe in this talk. Not too much. GILDA is a part of the activity of the Istituto Officina dei Materiali, which is based in Trieste, but has an antenna in Grenoble. And YOM in Grenoble means 10 staff people between researchers and technicians. We manage and develop instrumentation on 3 instruments, GILDA, Brisbane, and 13, but we also participate to the SRF and ILL governance bodies, scientific and logistical support to users, and we provide space in the office or labs. So the CNR is deeply involved in the activities in ILL and ESRF. Let's talk about a little bit this X-ray absorption spectroscopy. It's not a technique very known outside the synchrotron world, because you can do it only at the synchrotron. It's a technique that gives you information on the local structure around a given chemical species. So it's chemically selective and it's local. And you take out an absorption spectrum, and then from these wiggles here you can retrieve what's around the atomic species that is absorbing here the photon. And for local parameters you can get the nature and distance of ligands. So you can distinguish the ligands of your element, the site symmetry, distinguish whether it's octahedral or tetrahedral, and valence state, so we can make a speciation of your element. Samples can be in a large variety of forms, so solid, liquid, or even thin films at the level of the monolayer or lower, trace elements down to 10 ppm, just to give you an idea, organic and inorganic, and the nice thing is that we don't need any UHV and no fancy isotopes as it's needed in NMR of most power spectroscopies. Okay, this is an example of what work that has been done at GILDA in the field of biology for medicine. And this study about the interaction of cisplatin with human superoxide dismutase. This protein was found to aggregate in patients with ALS disease. And the laboratory tests shown that cisplatin could inhibit the formation of the new HSOD aggregates and solubilize the aggregates already formed. And the hypothesis was that cisplatin broke the bridge between these 2 sulfur atoms of 2 neighboring units of the superoxide dismutase. This was seen in crystal form by X-ray diffraction, but users wanted to know if this happens also in solution, that it's much nearer to the real situation. They came to GILDA, made an exact experiments in solution with a concentration of 600 micromolar, so they said real conditions. And these are the spectra, exaspectra with the superimposed structural model fit, and this was the model that we found. Actually, the cisplatin unit was attached to one part of the superoxide dismutase, and we could reproduce the structure at a high level of accuracy. So we could demonstrate that by EXAFS, cisplatin stuck to the superoxide dismutase molecule, a protein, and could actually hamper the 2 molecules come together and aggregate. And this was done in solution. And let's Now I will give you a little bit some information on the beamline. Okay, the beamline is a long construction with a big optic hatch that contains all the optic elements for X-rays, one experimental cabin for the XS experiments, and then a control room for remote control. Here are the main parameters. We can analyze all the elements you see in green, both of the, say, K edges or L edges, depending on the Z of the element. And the red elements will be reachable when we will have the LISA project running. The flux is sufficiently high to permit us to work in a diluted system. So typical dilution limits are, say, 10 ppm or 0.3 monolayers. And we can work in two conditions, optical conditions, high luminosity beam or low luminosity and lower beam. The access at GILDA happens through a submission of the experimental proposal via a web-based procedure on the SRF site. What is important is that we have two beam time quotas. One public beam time, 1/3 is controlled by SRF, but 2/3 of the total beam time are for Italian users. So GILDA is mainly dedicated to the experiments of Italian users. We have 4 deadlines. Public beam time is 1st September and March, and the Italian beam time is 1st May and November. In both cases, we have a selection of a review panel that be ESRF or Italian. And here you will find all the information about the new all the infos on the beamline. And not only beamline, we have also some facilities on site. We have a chemistry lab, some offices to host visitors, and this is the premises of the IOM Institute here in Grenoble, and we have also a guest house and canteen for the users. And this is the staff responsible, myself, my scientist Andrea Trapananti, and the postdoc Simone Torrengo. You can contact any one of us if you need help in preparing your proposals. And just to conclude, GILDA is the Italian CRG beam line at the SRF. It dedicates much of the time for Italian users, and it's mainly dedicated to X-ray absorption spectroscopy experiments, and X-ray absorption spectroscopy gives you local information around selected chemical species. For those who want to go deep inside on what we can do on GILDA, tomorrow at 2:30 here in Bicocca we'll have a longer presentation with presentations also for some users, and we'll see a little bit in more detail what you can do at GILDA. Thank you for your attention.
Questions?
I have a fun question. Who chose the name of your GILDA, LISA, which the next one?
In all cases, it was the beamline staff. The old beamline staff for GILDA, the present beamline staff for LISA. It's always a woman name. Are you not happy with that?
Well, that's the difficult choices. I mean, it's instruments names and the color of instruments too. That can be very tough decisions.
So how does this complement what you can do at Electra, for example? How does this fit in?
Okay, if we stuck to X-ray absorption spectroscopy,
yes.
Electra is more dedicated to lowest energies. So right. They can do, say, the sulfur K-edge, the K-edges of lighter elements.
So Electra does
there are beamlines that can go down the boron K-edge. Okay. And we start more or less from the 3D metals on. Okay. So we are complementary in this sense.
Okay, so I see no more questions, so we thank the speaker again. And we move on. I think it's clear. Claudia's turn, right? No? Yes. So, Claudia Mondelli.
I have to change computer.
She will tell us about neutron probe for geochemistry and environment. So probing the environment with neutrons.
I will change the configuration of everything just to make more complicated. No, okay, grazie. So somebody say that Macintosh is intelligent. I hope that. Okay. So thank you to the organizer to invite me for today. And come on. Now nothing happens. So maybe it's not so intelligent. Okay, everything changed. Voila. So I want to speak today about how to use neutrons in geochemistry in environment. Just to remember why neutrons. As somebody say, neutrons tell us where the atoms are and what the atoms do. So with neutrons, we can study both structure and dynamics. In particular, for the geochemistry or for environment, generally structure is much more important, but we can do some dynamics too. And if you think about the states of the, of the matter, we can have gas, some very ordered systems, or some disordered systems. So with neutrons, we can check dynamics of gas and some correlation in the time, and we can study the structure of ordered systems and study the structure and the dynamics of disordered systems. In particular, with diffraction, we can have different kind of results, and in particular, I will speak in some example about structure of disordered systems. So we can have a lot of different subjects where neutrons are really, different fields where neutrons are really important. You had some examples today, and in particular from the presentation this morning, you have seen that we can really have a very wide range of fields where neutrons are very important. For the geochemistry, I want to start with an example. It's about Mars. It's not Earth, it's Mars. So this is a very fun for me example because using simply diffraction, neutron diffraction, we were able to answer about what caused the magnetization around the Martian craters. So Mars is like Earth, has some magnetization in the planet with the map that has been done from NASA several years ago, and something bizarre happened because in the south of the planet, the core, the iron core of the planet is switched off. So it's just the magnetization comes from the crustal elements. And in particular, in the south, there's a strong magnetization of the planet, but around some craters is completely demagnetized. So why? what has been done is to study peroxide, because is from this material coming the magnetization on Mars, and the people study the effect of the pressure on the structure of this compound. And what we can see, because neutrons is able to see magnetic structure, so this is one typical application of neutrons. And what happens that when we apply a quite strong pressure in the direction 001 on the compound, the peak, magnetic peak, disappears. So demagnetization happens, and it's because the total magnetization of the compound comes from some differences of feeling of the different planes, and where in the planes we have antiferromagnetic coupling, and the total there is some ferromagnetism. But when the pressure is applied, this characteristic magnetization disappears because it's changing the structure. So this experiment allows us to see that probably the demagnetization comes from the impact produced on the Mars from meteorite. So with the simple experiment of neutrons, we can understand why we have this part demagnetized on the Mars. So another example is about the effect of pollution of pollutant like mercury. Mercury is a very high pollutant, and it's very dangerous for the human being because it induces a lot of disease, and in particular in the brain, in the mucosa, and something like this. And this pollution comes principally from the industrial emission and from the burning fossil fuels, but also from some organic pesticide and from mercury mining, and from also crematorium and incinerator and even volcanoes. And the typical way to be, intoxicated is eating fish, because it's present in the fish. So, and the effectiveness of the mercury to affect humans is because there is a particular effect of magnetization of the metal mercury in the food chain. So, in particular, there is a region in Guyana, in French Guyana, where this effect is very diffuse, and there is some meaning of gold and mercury, and this mineral in contact with the phreatic nerve and pass in the water, materials are really effective to change the mercury in the form of material that's very dangerous, and the fishes eat, the algae that are with this material, and there is an enhancement of the effect, and finally, starting from a very little quantity in material, we have a contamination of the human being. So the effect is really dramatic, because there is deterioration of the nervous system, so there is some impaired hearing, speech, vision, and gait, causing involuntary muscular movement. So it's really really dramatic, the effect. So what we studied is why the mercury is so dangerous. And this is, so the idea is in the human, in the nervous system, in the human being, in particular, the electric signals are, coming from the ions moving through the membrane. And this is possible when the ions with the hydration, the water hydration around, are tailored the sides of the channels. In particular, in the human, there is calcium and nickel ions that are typically used in the transmission of the electrical signals. So the idea was to compare this hydration shell of the mercury with, for example, cation of calcium. And the study has been done with an instrument dedicated to the structure of the amorphous systems. And in effect, what we can obtain from neutrons is the distances between mercury and oxygen and between mercury and hydrogen. We can obtain the number of coordination around the cells. So what we can see that this experiment gives us the idea that around the mercury, the cation mercury, there are 6 molecules of water, exactly very similar to the case of calcium. So the mercury is so dramatic, the effect, because in a certain sense, there is a mimicking of the calcium ions from the mercury. So the organism doesn't recognize the mercury as a foreigner and dangerous gas. And for this reason, the mercury is, accumulating in the organism, giving this effect of magnification. Just 2 words, because we are speaking about environment, about another study that is about the radioactive waste disposal. In particular, in France, there is a big attention to this point, and there are some regions where the radioactive waste are in the clay zone. And the problem is, with the passing of time, there is a reduction of the anaerobic reduction, corrosion of the steel tanks that produce hydrogen. So the idea is this hydrogen, start to rise the pressure of the hydrogen, and it could be dangerous during the years. And so we study what the hydrogen is doing in the clay, and in particular with dynamic measurements that we performed in ISIS, in Mari. And what we can see with this kind of measurement that we have hydrogen confined in micropores. We can obtain these results because there is an inelastic peak at low temperature that is not present when hydrogen is free. And we can see that there is, of course, a part of the hydrogen that is confined in mesopores. So because we can see here the typical rotational peak of the rotor of the hydrogen. So studying the quasi-elastic signal, we are able also to see how the hydrogen moves in the channels. So we can clearly say it's said that hydrogen is really in the porous and moving in diffusion, simple diffusion, and you have a free part moving like in just ballistic way, and the other part confined is moving with diffusion, like a thick diffusion. Combining that with some measurement of absorption at high level, we can see that the clay can reduce significantly the effect of the productive hydrogen in the right side. So I am at ILL if you want to contact me for, experiments, proposals, and so on, I'm available for you, and I will thank again the organizer. And you, of course, for to help me.
No questions. Okay.
Okay.
Then thank you again. Last speaker is this session is Alessandra. Ciao. Alessandra Gianoncelli from Elettra, and she will tell us on synchrotron radiation microscopies for the life sciences. Sì, sì, conviene spostarmi. Rimasto bloccata su. Ecco, perfetto.
Okay, thank you very much. I'm going to briefly speak about synchrotron radiation microscopy for the life sciences. I don't know, I'm sorry, but there is a little bit of change in the layout of the presentation because of the PowerPoint here. So I don't know how familiar you are with synchrotron radiation microscopy. One of the most common one is X-ray microscopy. That has been proven to be a very effective tool for life science applications. There are several publications, and especially soft X-ray transmission microscopy, when combined with emission microscopy, can provide very useful information for exploring morphologically complex matter, including biosystem as cellular and subcellular level. Of course, it should always be combined with correlative tools and techniques from laboratory techniques and other spectroscopic techniques and other microscopy techniques like electron microscopy. As in electron microscopy, the specimen preparation is a critical issue. The specimen preparation for X-ray microscopy is easier than in electron microscopy, but still it's a critical point of the experiment. Moreover, you should always consider that there may be some radiation damage induced by the use of X-rays. Another typical microscopy technique used at synchrotron radiation is infrared spectral microscopy. That has been used in many applications, life science applications. At the moment is limited to micrometric resolution, but there are some new development where probably in the near future we can go to nanometer resolution. And in this case you have no radiation damage, but of course the spatial resolution is worse than with X-ray microscopy. There are different kinds of X-ray microscopes. One of the typical ones that you can find in Elettra, also in ESRF, BESI, ALBA, and in other synchrotron is the full field X-ray microscope, where you have, basically is the analogous principle of transmission visible light microscope, where you have a condenser that is illuminating your sample, And then you have an objective lens creating a magnified image of your sample on a CCD camera. Since you get an image in a single shot that could be fraction of seconds or a few seconds, it's usually a very useful microscopy mode for fast imaging, so you can monitor changing in your sample dynamics. And if you have a suitable rotation stage, you can also perform microtomography. And with this system, according to the objective lens that you're using, you can go down till 50 nanometers spatial resolution. Another typical X-ray microscope is the scanning transmission one, available, for example, in Electra and in ESRF, where in this case you focus your monochromatized X-ray beam, usually with zone plate optics, on your sample, and then you collect the transmitted X-rays again with a CCD camera. And while you are scanning your sample in a raster scan, so you collect the X-rays point by point in the raster scan. If you have suitable energy dispersive detectors, you can also record the X-ray fluorescence emitted by the sample. So you can have simultaneously morphological and chemical information of your sample with micrometric or sub-micrometric spatial resolution. In particular, I'm going to show, I'm sorry about this mismatch, some results obtained with the twin-mic microscope of Electra synchrotron. This is how we acquire the images. So we use a CCD camera that is recording, for every pixel in the raster scan, is recording a frame. And then from this you can construct absorption images that are, of course, sensitive to density and thickness in your sample. These are some polystyrene spheres with different sizes. And at the same time, you can collect differential phase contrast images. So simultaneously, you have absorption and phase contrast images. And because of the, because of how the system is in twin-mic, we have 8 silicon drift detectors that are facing the sample, so we can also record the X-ray fluorescence emitted by the sample. We work in the soft X-ray energy range, so between 400 and 2200 dB. So we can detect light elements, the K lines from carbon till phosphor, so typical elements of organic matter and important elements for life science application. Moreover, we can detect the L lines of some transition metal like manganese, iron, cobalt, nickel, copper, and zinc, and also some M lines of some metals. I'm going to briefly show some applications. For example, we have some application in the nanotoxicology field where we analyze fibroblast cells from mice exposed to cobalt ferrite nanoparticles. Here you see the bright field image, the absorption, and the differential phase contrast image. This is 80 by 80 microns, and this was collected with 450 nanometers spatial resolution. And here you see the elemental maps of iron and cobalt ratio to the one of carbon, where you see then the location of the nanoparticles that are cobalt ferrite. So iron and cobalt are co-localized, so the nanoparticles are not separated in ions, and you can see that they are located in the perinuclear region of the cells. You can also guess the nanoparticle clusters from the absorption images itself, because you see a darker spots in the images. Moreover, with X-ray fluorescence, we could notice that for high concentration of nanoparticles, above 500 micromolar, we have an inversion of the ratio between iron and cobalt in the nucleus compared to the one that you have normally for the nanoparticles and in the perinuclear region. So there is a release of cobalt in the nucleus. You can also perform some higher resolution imaging. For example, in this case, we used 135 nanometer spot size. And this is the visible light image of these two cells. These are the absorption images collected at 900 dV, and these are the phase contrast images. So from absorption and phase contrast, you can detect some nanoparticle clusters and also some areas, brighter areas here, that looks like craters or hollows in the phase contrast images. And because of the different absorption and the structure of these vesicles, we hypothesized that these are lipid droplets, and this was verified by using red oil solution that specifically stain lipid droplets. And we noticed also that by increasing the concentration, the size and the number of these lipid droplets is increasing. This is another typical application of our X-ray microscope. We analyzed a section of lung tissues from patients that died because of asbestosis or mesothelioma, that is the cancer induced by the asbestos fiber. Here again you see a bright field and absorption image of an area of a lung tissue. This is 50 by 50 microns with a half a micron spatial resolution. And this is the distribution of oxygen, iron, magnesium, and silicon in the area. So you see the silicon is in the fiber, that is inside this structure, while you have accumulation of iron and magnesium on the fiber and in proximity of the fiber. Another recent application concerned the study of aluminum toxicity. Since aluminum, when it's present in acidic soil, can limit the growth of plants, so it becomes a problem for agriculture. And so plant biologists are interested in finding where aluminum is located, for example, in the roots of the plants, and how it's absorbed and uptaken by the plant. So this is a recent experiment that we've done with an Australian group, where we analyzed some section of roots, and we mapped them from the external part till the, let's say, the center, to see how the aluminum concentration and distribution varies. And here you see two examples. So this is the external area, and we took 3 maps. This is the absorption and phase contrast image of the external area, and you see the distribution of aluminum, magnesium, sodium, and the colocalization between sodium in green and aluminum in red. And this is this area, a little bit more internal. So again, you see aluminum, magnesium, sodium, and the colocalization between sodium and aluminum. So you see that the concentration of aluminum is clearly decreasing from the external part, going towards the center of the roots. You can also analyze food. For example, in this case, we analyzed wheat grains. This is 80 by 80 microns, and you have the absorption image and the distribution of carbon over oxygen, the zinc. In particular, these users from the biotechnology faculty of the University of Ljubljana were interested in studying the distribution of zinc inside the wheat. And also magnesium that is colocalized with zinc, and you can also map the iron that is partially localized with zinc and magnesium. You can combine X-ray microscopy with infrared spectrum microscopy. So from you can analyze the same areas, because we can prepare the sample in a way that is suitable for both microscopy. So you can analyze the same area with a worse spatial resolution, but from infrared that is non-destructive, you obtain information about proteins, lipids, cellulose, and so on. And then you can combine with the results that you obtain with X-ray microscopy. Of course, because X-ray microscopy causes radiation damage, you should always do first infrared microscopy and then X-ray microscopy. And this is just one last example, is a relatively new microscopy techniques based on coherent diffractive imaging, where you can perform X-ray microscopy in different ways. In this case, we did it in a lensless mode. So we removed the zone plate and we just use a 5-micron pinhole as a beam to define the beam. And then we scanned, for example, in this case, a cell by scanning it on a raster scan with a step size of 1 micron. So you have a 5-micron pinhole and you scan your sample with a 1 micron step size. So you are oversample in your scan, and then you have a diffraction pattern for every pixel in your raster scan. And by using suitable algorithm based on Fourier transform, you can reconstruct the illuminated area. So you can obtain the image of your cell. So from this diffraction pattern and the combination of different diffraction patterns, you obtain the image of your cell and you recover the phase and the modulus and the phase of your object. And if you do it at different energies, you can also perform some X-ray absorption spectroscopy. In this case, across the L edge of iron, we did it across. And with these techniques, you can get a spatial resolution higher than the spatial resolution given by the optic of your system. So from a 5-micron pinhole, in this case, we obtained an image with a spatial resolution better than 200 nanometers. If you use an optical elements like a zone plate, again, you can improve even more your spatial resolution. And with this, I will stop the presentation. I hope I gave you some application of X-ray microscopy and infrared microscopy with synchrotron radiation techniques. Thank you.
Curiosity, how do you prepare the samples for your experiments?
It depends on the sample. For example, for cells, usually they are fixed with paraformaldehyde 4% on silicon nitride windows, 100 nanometer thick, so they are basically transparent for X-rays, and the cells are grown directly on the silicon nitride windows. For tissues like lung tissue or plant tissue, they are usually or embedded in a resin like EPON or sometimes paraffin, and then they are sectioned at
like
thickness.
40
Sorry?
Like 40 TEM for the
yes,
transmission.
But we can use thicker samples because X-rays are more penetrating. So the thickness varies according to the sample. It could be a few microns till 25 microns. So the sample preparation is similar, but we don't need to put a metallic coat on the samples, and they can be thicker than electron microscopy.
Okay, thank you.
What about the radiation damage? Do you cool down the samples, or?
In the twimic microscope, we don't cool down the sample, but one of the techniques to slow down the radiation damage would be to have a cryo stage. We actually see radiation damage on the samples, of course, especially, it depends on the dose, of course. If it's a fast imaging is not so high, but if we do X-ray fluorescence, we'll see radiation damage.
Any more questions or comments? No? Then we thank the speaker again.
Thank you.
And with this, we move on to the next, which is Module D.
So, Carla.
So how would you like to do it? I mean, you
think,
stand, you
we
can
are
stand, or
going
you
briefly-
can sit, you can,
We are going briefly
as you are more comfortable.
quickly through the procedure and
Okay, now then. First of all, this material, this Module D PDF file is available on the website of the Roadshow. Therefore, I will just briefly use it to spot on some points that might be of particular interest in case application is needed and necessary, as we hope is going to be, of course, for facilities. More or less, I have to say, all facilities have a similar approach. And basically, I'm referring to the SRF because it's the one I'm more familiar with, and Carla might give you glimpses on the neutron sources as well. There are different types of proposals. Actually, Francesco was very clear on the CRG applications, public peer-reviewed proposals, and proprietary research proposals. If you are a firm of some sort, or if you if you are in the position, if you're not willing to disclose the results of your work. So public peer-reviewed proposals, different panels. So your first point would be decide which is the category you are referring to. If you are interdisciplinary, you decide what's better. And as you see, the time in ESRF, this is the pie graph describing how beam time is distributed across the different disciplines or panels. Macromolecular crystallography has a significant share of the pie, but I mean, all different categories and panels have relatively, what can I say, a good allocation. You just have to decide what is your main field. And in doubt, my experience is ask. The point is that really people at facilities are there to support you. They are scientists, as we said before, and they are incredibly helpful. Amazingly enough, they do answer mails efficiently. So if you are thinking that you may need one of these sources, facilities for your experiment, the fastest way is ask the scientist. And typically, since they are very interested in being original and having results, they will answer and give you very good advice. So my advice is ask for advice. As you can see, the beam time allocation is competitive, and again there you have to try to write the most efficient, the clearer and detailed, motivated application. So you need to talk with your beamline scientist or talk with your colleagues and write your application. Okay, as for never be scared by the proposal. It's simpler than it looks. Once you get used to it, if you have a colleague nearby, it's going to take a short time to fill it in. The most important bit is the science. Okay, this is specific to protein crystallography, beam allocation group, beam time allocation groups, but I don't think that that's a problem, because if you're a crystallographer, you know about bags. If you're not a crystallographer, you're not interested in bags. It's a beam time allocation group. Since for protein crystallography, the type of usage of the experimental time is very intensive. You have very short slices. Sometimes you need only a few hours, but you need them regularly. You may need them once a month or so. There would be no point in sending 12 different applications. Different groups join together, and there is a beam time allocation which within the group is flexibly allocated. And that works well, provided you don't fight for the 15 minutes remaining or coming. But normally it works, if people are not too greedy. This is the mysterious process which at last I knew something about how beam time is, how they do decide to give you beam time or not. And it involves feasibility, assessment by assessment group, and there are several committees. All this is somewhat a black box for users, and you just come up with the decision. But again, you can ask, and you will be given a very good reason if your application failed, and they will support you to write a better application. So asking is good. And the main point is you will have to publish and to, of course, acknowledge participation having been granted beam time, because it's what synchrotrons have to produce, science, knowledge, and papers as well. And there is this peculiar category that is proprietary research. Now, there might be reasons for you as a scientist for keeping your research to yourself, but typically we want to publish. Of course, there are cases in which this is not really the goal. The goal is having results to produce your patent, to develop a new product, to produce a protocol. And indeed, as you can see from this very rich, multicolored slide from ESRF, I think, several firms do buy synchrotron time in some cases if they really want to keep the results to themselves, or they do collaborate with synchrotrons, given the fact that, or neutron source, of course, because there are several assets that these facilities can offer, not just their beam time, but also in scientific support, collaborative experiments, defining a protocol. And you can aim, and in these days, in these dark times, this is more and more necessary, aim to have a collaboration between an industry, academic, not-for-profit, and the facility. And all this happens, and it works, and it may even allow you to have a bit more money to do your science. And here are some fancy examples, and each source has its fancy example, from relevant engineering that makes us safer when we fly to synchrotrons, batteries, and my God, this is not my field, but anyway, you need to trap hydrogen in some way if you want to use it for fuel, and you have to start materials and devices for that, and what better than neutrons and X-rays for that? Building, of course, protein crystallography, which is indeed one of the most relevant actors in the field of drug design. And there are a number of activities which very efficiently are carried out for ESRF. I can think about Ed Mitchell, who is in charge of that, and I'm sure that all major facilities have dedicated and smart staff for that. So there's always a industrial liaison office in these facilities, and again, productive, successful, and these days, of course, the EU is very keen on having science as productive as possible, also on the industrial side. So I guess this is going to be more and more the case for the future, that we have to show to be useful on top of being simply useful. And this is us, of course, because we are acting again as some sort of incubator or connector. And this was the end of it, and it's time for the neutron people to give their...
Well, what I will say, very little in addition to what she just presented to you, is that in this other example, ISIS and then later ILL, essentially the scheme is the same. There are twice a year, in the case of neutrons, time of the year when users can apply for beam time, and again with some similar advices that she just told you about. If you have any doubt, you just talk with the instrument scientist, write to them, and even if you have missed the call, maybe you can apply in different scheme like express request that I'll show you in a moment. This PDF file will be available on the web. So in case you want to look carefully, you can download it from the web. But essentially, there are these two calls for proposals, and as she was saying before, the most important is the science content of these two pages, and the sample environment if you are going to do very high pressure, high temperature, high field, magnetic field experiments. But there are also now, there is a growing portfolio of opportunity for rapid access, express access, which will give the users the opportunity of really essentially use, inverted comma, the facility all over the year. And in those, the industrial access, which is a little bit different from facility to facility. For instance, in this case, there is also there is also the recent possibility of doing the experiment and see the results in advance before deciding whether it would be commercial in confidence or not, which I think is also going to be used at the SRF soon. I don't know about Elettra and about ILL. I think it's not used there yet, but probably will be something which will be explored. Here is the same colored example of some of the this is dated back to 2013. We haven't updated because these are things which really keep updating frequently. And behind all this, in all the four facilities, there are offices which assist the user, not only from the point of view, of course, of the science, but there is a user office which assists the user from the point of view of the logistics, in helping them in finding transport and hotel. And the last thing I would like to show, not just the Italian use, because I think we have already heard about that. I want to go a little bit again for ILL and show how really similar kind of standard, I would say, there are now all over the facility. Not only, even if the neutron and little laboratory area are different from the synchrotron radiation, in a way there is a sharing of method towards the users, which is becoming more and more common. So what I would like to talk about a little bit is sorry, these are very, I want to go to the dissemination, which is something, yes, the training, more than the dissemination, the training. I think another important point is the training that all these facilities have, synchrotron radiation and neutrons. The Hercules school is very popular and joint school neutron and synchrotron radiation training, long, I think is about 2 weeks. And, sorry? It's about a month now. Ah, okay. Okay, so you probably get married during the, I mean, you find, yeah, there are cases, good. So this is really the most important and traditionally very established school. But there are also a large number, and equally important, I think, schools and training schools, which are, and here I'm pointed out to the main ones regarding this facility, which are the Oxford Neutron School and the ISIS Training School, plus the Italian school, which are associated to these agreements that Italy has with ESRF, ILL, ISIS, and Elettra. I mean, in this case is the CNR, because Elettra is in Italy. But I mean, these are really the places where the young PhD students are contaminated with all this kind of activities. So I think if you don't have, I mean, if you have questions about the access and the training, we are very, very happy to try and answer.
It's because Robert is here. It's about, for me, it's really, a puzzle. The fact that when you have the same proposal around all of the facilities, and so what do you think about if it's possible to think with general way to, in a certain sense, have a sort of control about that?
Most facilities are, I mean, proposals to facilities are in confidence. Okay? So they're in confidence. So like any funding proposal, they're taken in confidence. So the panels who select them do it in confidence. It is, which is where you have the problem, is people submitting the same proposal to multiple facilities and may sometimes get multiple time, which means they're taking time away from other users.
Yeah.
Okay. Now, I don't know what happens with synchrotron facilities. I know, for example, with the ILL, I share information in confidence with the ILL director, and I also do the same with the SNS director in the States. So that's definitely, so we can tell if there are multiples. I don't know if anybody else does this. Typically speaking, we know the culprits. We know the guilty people who do this. So we know very, which is not fair, to be honest. If you send your same proposal to multiple places and you get approved in one place, you should withdraw from the other place. The people who don't do that, and then they have multiple time which they use for different things, that is not fair. And if we find people doing that, we will punish them accordingly.
From myself is to write clearly.
Yeah,
if this is already proposed, but I know that it is not typical.
No, this is what most of the users do, to write clearly.
Most proposal forms will ask the question, has this been submitted somewhere else? But of course, it doesn't give you the answer, has it been approved? Okay. So.
You want faithful users, but I mean, being a user, maybe you want your proposal to be approved somewhere. And if you have to submit it sequentially to all different sources, it would take ages before it's approved or been.
This is fine. Submitting it to multiple facilities is fine, as long as you tick the box saying you've done so. And if you get feedback from one facility,
then you tell the other facility that it is the Western vision.
Same thing in multiple times, and then they'll do the experiment here, and they'll do something else there. This is going around the system.
And that's what they are talking about. Yeah. Yes.
Scientists are among the most honest people I have ever met in my life. Altogether. I mean, compared to the rest of the planet, we are amazingly nice. Please. Well, I mean, in other jobs, in other categories, say politicians compared to scientists. Priests, what is a category that is actors,
we won't go any further.
Artists,
I have
whatever.
a different theorem than it's Chipolo's theorem that any category you take, you get the same distribution.
More or less.
I like science.
That's clear.
Anyway.
We do.
Hooks. Even better. Even better than science.
Okay. If there are no any other questions, I think we can close.
I think you are the chairman.
No, well, Giuseppe has been the chairman the whole day. So if there are no any other questions, I want to thank all the speakers and the attendees. And the next roadshow will be in Cosenza on the 1st, so tomorrow. No, on the 2nd, not tomorrow, on the 2nd. So thank you.